Imagine waking up to a completely broken project, realizing that months of work have disappeared, or that a teammate's mistake has overwritten everything you did. For most developers, this is an absolute nightmare. A moment of panic where you feel totally lost. But why do we fear Git? Why do we treat it like a guessing game, typing commands and hoping for the best, only to panic when something goes wrong? The truth is, Git is not a mystery. It is just a simple database. By looking under the hood, understanding how it actually saves your files, and learning how it links your history together, you will go from feeling anxious to being in complete control. You will never fear a broken codebase again, because you will know exactly how to fix it from the inside out. Appreciating Git's write-only, content-addressable design requires us to look at how it differs from older version control systems like Subversion or Perforce. Traditional systems are delta-based. They think of the project as a base set of files and store the changes made to each file over time as a list of differences or deltas. This means that to reconstruct what the project looked like at version 5, the system must start with version 1 and apply each subsequent delta in sequence. Git rejects this model entirely. Git thinks of its data more like a stream of snapshots. Every time you commit or save the state of your project, Git takes a picture of what all your files look like at that moment and stores a reference to that snapshot. To be efficient, if a file has not changed, Git does not store the file again. Instead, it just stores a link to the previous identical file it already has. This subtle shift in perspective, treating history as a collection of complete snapshots rather than a list of incremental patches, is what makes Git extremely fast for branching, merging, and looking back in time. Every Git repository is organized around 3 primary logical areas, often referred to as the 3 trees. These are the working directory, the staging area, and the Git directory. Understanding the interaction between these 3 spaces is the key to mastering Git operations. The working directory is the single checkout of one version of your project. These are the actual files on your computer's hard drive that you can open, edit, and delete in your text editor. It is a temporary workspace where you can make experimental modifications without immediately affecting the repository's history. The staging area, historically and technically referred to as the index, is a highly optimized binary file located inside your local Git directory. It serves as a preparation zone. It is a blueprint of what will go into your next commit. Unlike older systems where committing immediately packages up all changes in your working directory, Git forces you to explicitly choose which changes you want to include. When you run git add, you are taking a snapshot of a file in its current state in the working directory and copying it into the staging area. The Git directory, which is the hidden .git folder at the root of your project, is where Git stores the metadata and the object database for your project. This is the actual repository. When you clone a repository, this is the part that is copied from the server to your machine. When you run git commit, Git takes the snapshot currently in your staging area and permanently writes it as a commit object to this local database. This architecture creates a very specific lifecycle for files in your project. A file can be either tracked or untracked. Untracked files are files in your working directory that were not in your last snapshot and have not been added to your staging area. Git will not include them in commits or pay attention to them unless you explicitly tell it to. Tracked files are those that were in the last snapshot. They can be unmodified, modified, or staged. Upon cloning a repository for the first time, all project files start as tracked and unmodified because they have just been checked out and made without edits. As soon as you edit a file, Git detects that the file on your disk differs from the version in its database, and the file transitions to the modified state. If you decide this modification belongs in your next release, you stage the file. It is now staged. Finally, when you commit, that staged version is written to the database, and the file returns to the unmodified state, waiting for your next round of edits. Grasping what happens during a commit starts with looking at how Git represents content. Git is fundamentally a content-addressable file system. This means that at its core, Git is a simple key-value store. When you insert any piece of content into Git, it returns a unique key that you can use to retrieve that content later. This key is a 40-character hexadecimal hash. Historically, Git has used the SHA-1 hashing algorithm, which produces these 40-character strings based on the content of the data plus a small header. Modern Git is transitioning toward SHA-256 for enhanced security, but the fundamental mechanic remains the same. Because the key is generated mathematically from the exact content of the file, any change to the file, even a single character or space, will result in an entirely different hash. This ensures complete data integrity. It is impossible to alter a file or change its name without Git knowing about it, because doing so changes the hash. Every time you commit, Git does not just store your files. It creates a hierarchy of objects inside its database. First, for every file in your commit, Git creates a blob object. A blob stands for binary large object. A blob stores the raw contents of a file, but notably, it does not store any metadata. It does not store the file's name, its folder path, or its permissions. It only stores the data itself, compressed with zlib. Git organizes these blobs into folders and links them to file names by creating tree objects. A tree object corresponds to a directory in your project. It contains a list of entries, where each entry contains a pointer to a blob or another tree, along with the mode, the type, and the file name. If your project has a root folder containing a source folder, which in turn contains a main file, your commit will be represented by a root tree pointing to a source tree, which points to the blob containing the main file's content. Finally, Git creates a commit object. The commit object is the top-level metadata wrapper. It contains a pointer to the root tree object, representing the complete snapshot of the project at that exact moment. It also contains the name and email of the author, the name and email of the committer, a timestamp, and the commit message you wrote. Crucially, the commit object also contains a list of parent pointers, which are the hashes of the commits that came directly before it. A standard commit has one parent. A merge commit has two or more parents. The very first commit in a repository has 0 parents. By linking commits to their parents, Git builds a continuous chain of history. This chain is a directed acyclic graph. Because each commit points backward to its parent, you can trace the history of the project all the way back to the beginning by following these pointers. This graph-based design explains why branching in Git is extremely lightweight compared to other version control systems. In older systems, creating a branch involves making a physical copy of the entire project directory on the server. This is slow, takes up a massive amount of disk space, and makes merging a nightmare. In Git, a branch is not a physical copy of files. A branch is nothing more than a simple, lightweight, mutable pointer to a specific commit in the history graph. Initializing a repository prompts Git to create a default branch pointer, historically named master, and increasingly named main. This branch pointer is just a small text file inside your local .git folder that contains the 40-character hash of the commit it currently points to. When you create a new branch, Git does not duplicate your files. It just writes a new text file with the name of your branch and writes the hash of your current commit inside it. You now have two branch pointers pointing to the exact same commit in your graph. This operation is virtually instantaneous and consumes only 41 bytes of disk space. Tracking your active branch is the job of a special reference called head. Head is a pointer that usually points to the local branch pointer you are currently on. For example, if you are on the main branch, head points to the main branch pointer, which in turn points to a commit hash. When you make a new commit, Git performs a very specific sequence of events. First, it writes the new blobs and trees for your stage changes. Then, it creates a new commit object, setting its parent pointer to the commit hash currently pointed to by head. Finally, Git updates the current branch pointer, the one head points to point to this brand new commit hash. Because the branch pointer moves forward automatically with every commit, head moves with it, ensuring you are always looking at the latest snapshot. Checking out a specific commit directly instead of checking out a branch points head directly to that commit hash rather than to a branch pointer. This is what is known as a detached head state. It sounds intimidating, but it is actually very simple. It means that any new commits you make in this state will not update any branch pointer. They will point back to their parents, but no branch pointer will point to them. If you switch back to your main branch, these new commits will become orphaned in the graph. Since there are no branch pointers pointing to them, they are no longer reachable. Merging is the process of bringing two diverged lines of history back together. When you want to merge one branch into another, Git has to determine how to combine their changes. There are two primary types of merges: fast-forward merges and three-way merges. A fast-forward merge occurs when there is no divergence between the two branches. Imagine you have a main branch pointing to commit A, and you create a feature branch. You make two commits on the feature branch, taking it to commit C. Meanwhile, no new commits have been made on the main branch. It still points to commit A. In this scenario, the history of the feature branch is a direct linear descendant of the main branch. When you switch to main and merge the feature branch, Git realizes that it does not need to perform any complex conflict resolution. It just moves the main branch pointer forward in the graph to point to commit C. This is a fast forward. No new merge commit is created because the history remains completely linear. A three-way merge occurs when the histories of the two branches have diverged. Imagine you branch off main at commit A and write commit B on your feature branch. At the same time, another developer pushes commit C to the main branch. Now, the main branch points to commit C, and your feature branch points to commit B. They have a common ancestor, commit A, but their paths have diverged. When you merge the feature branch into main, Git cannot just move the pointer forward. Instead, it must perform a three-way merge. This process involves Git analyzing three specific snapshots in the graph: the snapshot at the tip of the first branch, which is commit C, the snapshot at the tip of the second branch, which is commit B, and the snapshot at the nearest common ancestor of both branches, which is commit A. Git compares the changes in B and C relative to the common ancestor A. This allows Git to figure out which changes were made on each branch. If a file was modified on branch B but not on branch C, Git automatically takes the version from branch B. If a file was modified on branch C but not on branch B, Git takes the version from branch C. If Git can resolve all differences automatically, it creates a new snapshot combining the changes and writes a special commit called a merge commit. This merge commit is unique because it has two parent pointers instead of one, linking both branches of history together. However, if the exact same line of the exact same file was modified in different ways on both branches, Git cannot automatically determine which version is correct. This is a merge conflict. When a conflict occurs, Git pauses the merge process, leaves your working directory in a partially merged state, and marks the conflict directly inside the affected files. These conflict markers are easy to recognize. They begin with a series of less than symbols followed by the name of your current branch, indicating the changes from your checked out branch. This is followed by a separator of equal signs, and then the changes from the branch you are trying to merge in, marked by a series of greater than symbols and the name of that branch. To resolve the conflict, you must open these files, decide which code to keep, manually delete the conflict markers, stage the resolved files, and run git commit to complete the three-way merge. While merging combines the histories of two branches, Rebasing offers an alternative way to integrate changes by rewriting history. The fundamental goal of Rebasing is to maintain a clean, linear project history. Imagine the same scenario where your feature branch diverged from main at commit A. Main has moved forward to commit C, and your feature branch has moved forward to commit B. Instead of merging main into your feature branch, which would create an extra merge commit and clutter your history graph, you can rebase your feature branch onto main. Running a rebase triggers a sequence of background steps to replay your work. First, it identifies the common ancestor of both branches, which is commit A. Next, it looks at all the commits made on your current feature branch since that ancestor, which is commit B. It takes those commits, temporarily saves them to a temporary area, and resets your current branch pointer to point to the tip of the target branch, commit C. Finally, Git takes each of the temporarily saved commits and attempts to apply them, one by one, on top of commit C. During this playback process, Git is not just moving the original commits. Remember, commits are immutable. Their hashes are calculated based on their content, parent pointers, and timestamps. Because the parent of commit B has changed from commit A to commit C, Git must generate a brand new commit, which we can call B'. B' has the same file changes as B, but it has a different parent pointer, a different timestamp, and therefore a completely different SHA hash. Once all commits are successfully played back, Git updates your feature branch pointer to point to the tip of this new linear chain. Rebasing makes your history look as if you did your work sequentially, even though you worked in parallel. However, this power comes with a critical warning, often called the golden rule of rebasing. Never rebase commits that you have already pushed to a public repository. Because rebasing rewrites history by generating brand new commits and abandoning the old ones, anyone else who has pulled your original commits will now have a history that diverges from yours. If you push your rebased branch back to the server, you will be forced to use a force push, which overwrites the remote repository's history. When other developers attempt to pull, Git will try to merge their local copies of your old commits with your new rebased commits, resulting in a chaotic mess of duplicate commits and endless merge conflicts. Use Rebase to clean up your local work before you share it, but once it is shared, treat history as read-only. Collaborating with other developers requires moving beyond our local repository to work with remotes. A remote repository is just a copy of your project hosted on a server, which could be on GitHub, GitLab, a private server, or even a different folder on your local machine. Cloning a repository automatically sets up Origin as your default remote connection, mapping it to the original URL. Git manages collaboration through remote tracking branches. These are read-only references that behave like bookmarks, showing you exactly where the branches on the remote server were the last time you communicated with it. Remote tracking branches live in a special namespace, usually named origin/branch name. You cannot move these pointers yourself. They only move when Git performs network operations to synchronize with the server. There are two primary commands for retrieving changes from a remote: fetch and pull. It is crucial to understand the difference between them. Executing git fetch tells Git to reach out to the remote server, scan for any new commits pushed since the last connection, and download them to your local database. It then updates your remote tracking branches, such as origin/main, to point to the latest commit on the server. Crucially, git fetch does not modify any of your local branch pointers or change your working directory. It is a safe, read-only operation that just updates your local copy of the remote state. It allows you to inspect what others have done before deciding how to integrate their work. In contrast, git pull is a shortcut command. When you run git pull, Git internally runs git fetch to download the latest changes, and then immediately runs a second command, usually git merge, to merge the remote tracking branch into your current local branch. If you prefer a linear history, you can configure git pull to use rebase instead of merge by adding the rebase flag. This will fetch the changes and then rebase your local unpushed commits on top of the newly fetched remote changes. When you want to share your work with the world, you use git push. This command takes your local commits, uploads their associated blobs, trees, and commit objects to the remote server, and then updates the corresponding branch pointer on the server to match your local pointer. Git will only allow a standard push if your local branch is a direct descendant of the branch on the remote server. If another developer has pushed changes to the remote branch while you were working locally, your histories have diverged. In this case, Git will reject your push, warning you that the remote contains work that you do not have locally. To resolve this, you must first fetch and integrate the remote changes into your local branch, resolve any conflicts, and then push again. As your project grows, you will want to mark specific points in its history as important. Git provides tagging for this exact purpose, which is most commonly used to mark release points like version 1.0. There are two types of tags in Git: lightweight and annotated. A lightweight tag is very similar to a branch, but with one critical difference. It is immutable. It is just a pointer to a specific commit stored as a file in the .git/refs/tags directory. It never moves. When you create a lightweight tag, you are merely giving a friendly, permanent name to a commit hash. An annotated tag, on the other hand, is stored as a full object in the Git database. When you create an annotated tag, Git writes a tag object containing the tagger's name, email, date, a tagging message, and a pointer to the target commit. This tag object is then hashed, and Git signs it if you configure it to do so. Annotated tags are highly recommended for public releases because they store complete metadata and are cryptographically verifiable, ensuring the integrity and authorship of your release points. As you become more comfortable with these commands, you might find typing long Git commands repetitive. Git provides an alias system that allows you to customize and shorten your command line experience. You can configure these in your Git config file. For example, you can alias checkout to co, status to st, or create highly complex aliases that output beautiful, color-coded, ASCII representations of your commit graph directly to your terminal. This is not just a convenience. It allows you to build highly personalized workflows that match your exact mental model of the repository. Hosting repositories and collaborating at scale demands an understanding of how Git operates in a server environment. A Git server is fundamentally simple. It does not require a complex running process or a heavy database engine. It only needs to store what is called a bare repository and provide a way for clients to read and write to it. A bare repository is a Git directory that does not have a working directory. In your local development folder, you have a .git directory containing all the history and a working tree of files surrounding it. On a server, there is no need to edit files, so a working directory is unnecessary overhead. A bare repository contains only the contents of the .git folder itself, directly in the root directory. By convention, bare repository folder names end with a .git extension. There are 4 protocols that Git can use to transfer data between the client and the server: local, secure shell or SSH, Git daemon, and HTTP or smart HTTP. The local protocol is used when the remote repository is on the same disk or mounted over a local network share. This is common for small teams sharing a directory or for testing setups on your own machine. While fast and easy to set up, it is vulnerable to physical drive failure and often suffers from performance bottlenecks over slow network mounts. The SSH protocol is the most common protocol for write access in professional settings. SSH is secure, encrypted, and highly authenticated. Because SSH is a ubiquitous system tool, most servers already have it installed, making administration straightforward. To access a server over SSH, you must generate an SSH key pair on your local machine. This is done using utilities like SSH Keygen, which generates a private key that you keep secret and a public key that you copy to the server. Git uses modern, highly secure key algorithms like ED25519 or more traditional RSA keys. When you push or pull over SSH, Git authenticates your identity using this key pair, ensuring that only authorized developers can modify the codebase. The Git daemon protocol is a lightweight, unauthenticated service that comes packaged with Git. It listens on a dedicated port and serves repositories without encryption or access control. Because there is no authentication, it is extremely fast, but it is highly insecure. It is typically used only for open-source projects where anyone is allowed to read and download the code anonymously, but writes are strictly blocked. The HTTP protocol exists in 2 forms: dumb HTTP and smart HTTP. Dumb HTTP is a simple legacy protocol that serves Git files directly from a standard web server like Apache or Nginx as raw files. It requires no special Git-specific software on the server, but it is extremely slow and inefficient, as the client must request individual loose object files one by one. Smart HTTP has largely replaced its predecessor. It allows the client and server to negotiate data transfer intelligently, similar to SSH. When a client connects over Smart HTTP, the server runs a backend helper script called Git HTTP backend. This process dynamically packages the precise objects the client needs into a single stream, making transfer extremely efficient. It is highly popular because it works seamlessly through standard web ports like 80 and 443, allowing developers to bypass strict corporate firewalls that block SSH ports. While you can run your own Git server manually by setting up a bare repository on a Linux server and managing SSH keys in an authorized keys file, most organizations prefer a dedicated management platform. These platforms fall into two categories: self-hosted and software as a service. For self-hosting, tools like GitLab and Git provide comprehensive web interfaces, code review pipelines, issue tracking, and fine-grained access controls that run on your own private infrastructure. For software as a service, third-party hosted options dominate the industry, with GitHub being the most prominent. These platforms do not alter how Git works under the hood. They wrap the underlying Git command line and server mechanics in a rich, collaborative ecosystem. When working in a distributed environment, the way teams structure their contribution patterns is called a distributed workflow. Unlike older centralized systems where every developer commits directly to a single central repository, Git is fully distributed, meaning every developer has a complete copy of the entire history database on their machine. This unlocks a variety of flexible workflow models. The simplest model is the centralized workflow. In this model, there is a single central repository, and every developer has direct write access to it. Developers pull the latest changes, make their commits locally, and then push them back to the server. If another developer has pushed changes in the meantime, the push is rejected, forcing the developer to pull and merge before pushing again. This works well for small teams, but quickly becomes chaotic as the team scales, leading to push races and messy commit histories. For scaled collaboration, teams often adopt the Integration Manager workflow, especially in open source and enterprise settings. This is the model popularized by platforms like GitHub. In this workflow, there is a single official read-only repository, often referred to as the upstream repository. Developers do not have write access to upstream. Instead, they create a personal copy of the upstream repository on the server, a process known as forking. Developers clone their personal fork to their local machine, make their changes, and push those changes back to their personal remote fork. To integrate these changes into the official upstream repository, the developer opens a pull request, also known as a merge request. The integration manager, who has write access to the upstream repository, reviews the changes, requests modifications if necessary, and ultimately merges the pull request into the official codebase. This model keeps the production branch highly protected and ensures that every line of code is reviewed before it enters production. For massive, global open source projects like the Linux kernel, the dictator and lieutenants workflow is used. This is a hierarchical model designed to scale to thousands of contributors. At the top of the hierarchy is the dictator, who maintains the official main repository. Beneath the dictator are lieutenants, who manage specific subsystems of the codebase. Ordinary contributors write code and submit it to their respective lieutenant's repository. The lieutenant reviews and merges these changes into their subsystem branch. Finally, the dictator pulls the approved branches from all the lieutenants and merges them into the master repository. This keeps the review process highly distributed, ensuring that no single individual becomes a bottleneck for a massive engineering effort. Supporting these workflows is made possible by platforms like GitHub, which offer advanced administrative tools. Beyond simple code hosting, GitHub provides robust user account and organization management. Organizations allow you to group multiple repositories, manage team permissions, and establish strict branch protection rules. These rules are critical for modern software delivery. You can configure GitHub to prevent any developer from pushing directly to your production branches, requiring all changes to go through a pull request. You can also enforce policies that require pull requests to receive a specific number of peer reviews, pass automated testing suites through continuous integration pipelines, and maintain up-to-date linear histories before they are allowed to merge. GitHub also allows you to automate and script your workflows using its APIs and CLI tools. The GitHub Command Line Interface, or GH, allows you to interact with your pull requests, issues, and repository settings directly from your terminal. For deeper automation, GitHub provides both REST and GraphQL APIs, allowing you to write scripts that automate repository creation, user onboarding, and release management. This integration of raw Git mechanics with rich collaborative platforms is what powers modern DevOps practices. As you master these workflows, you will find yourself needing more advanced tools to manage complex scenarios. Git provides a suite of advanced features designed to help you navigate, debug, and repair your repositories. The first of these is revision selection. When you want to refer to a specific commit, you do not always have to copy and paste its full 40-character SHA hash. Git offers several convenient ways to refer to commits. First, you can use short SHA hashes. As long as the prefix you provide is unique within the repository, Git will understand which commit you mean. Usually, 7 or 8 characters are more than enough to be unique. Second, you can refer to commits relative to other commits using the caret and tilde symbols. These are extremely powerful for navigating history. The caret symbol, written as a commit reference followed by a caret, means the first parent of that commit. For example, head caret refers to the commit that came directly before your current commit. If you are looking at a merge commit which has 2 parents, head caret 1 refers to the first parent, which is the branch you were on when you merged, and head caret 2 refers to the second parent, which is the branch you merged in. The tilde symbol, written as a commit reference followed by a tilde, means go straight back this many generations, always following the first parent. For example, head tilde 3 means the great-grandparent of your current commit. It is a shortcut for writing head caret caret caret. Another advanced tool is interactive staging. Often, when you are working on a feature, you write code, add debugging statements, and clean up formatting all at the same time. If you run a standard git add, you stage all of these changes together. Staging interactively using the git add patch flag tells Git to break changes down into hunks. Git presents each hunk to you one by one and asks if you want to stage it. You can choose to stage the hunk, skip it, split it into even smaller hunks, or even manually edit the hunk on the fly. This allows you to construct beautiful, highly cohesive commits where each commit does exactly one logical thing, even if your working directory is a storm of miscellaneous edits. Getting interrupted in the middle of a feature with uncommitted work will block branch switching if those changes would be overwritten. Git will block you from checking out another branch if those changes would be overwritten. To resolve this issue, Git introduces a storage mechanism called stashing. When you run git stash, Git takes all the modified, tracked files in your working directory and your staged changes, and saves them to a temporary stack of incomplete changes. It then resets your working directory and staging area to match the head commit, leaving you with a completely clean workspace. Under the hood, Git stash is actually creating a set of temporary commits on a special reference called ref/stash. When you have finished your hotfix on the other branch and return, you can run git stash apply to restore your saved changes back to your working directory, or git stash pop to restore them and simultaneously remove them from the stash stack. Keeping your working directory free of build artifacts and temporary files is done via git clean. While the .gitignore file tells Git which files to ignore completely, Git clean allows you to actively find and delete untracked files from your working directory. Running git clean with the force flag will permanently delete these files, while adding the directory flag will remove untracked folders as well. It is a powerful way to reset your workspace to a pristine clone state. For security-conscious environments, Git supports cryptographically signing your work. Using GPG, SSH, or S/MIME keys, you can sign your commits and tags. When you sign a commit, Git signs the commit's metadata and writes your cryptographic signature directly into the commit object itself. On hosting platforms like GitHub, signed commits are marked with a verified badge, proving to your team that the commit was genuinely written by you and has not been tampered with since its creation. This prevents identity spoofing in sensitive codebases. When searching your codebase history, Git provides extremely fast search tools that operate entirely offline. The command git grep allows you to search for specific strings or regular expressions across your entire working tree, or even across historical commits, without needing to check them out. Searching the commit history itself is possible using git log with the uppercase S flag, commonly known as the pickaxe option. This search is unique. It does not just search for a string in commit messages. It searches for commits where the number of occurrences of a specific string in the actual code changed. This is extremely useful for finding the exact commit where a specific function or variable was first introduced or deleted from your codebase. Eventually, you may need to rewrite history deeper in your graph than your last commit. While git commit --amend allows you to easily modify your very last commit, modifying older commits requires an interactive rebase. By running git rebase with the interactive flag and specifying a parent commit, Git opens a list of your commits in a text editor. This list is a plan of action. Each commit is prefixed with a command. By default, the command is pick, which keeps the commit as is. You can change pick to reword to change a commit message, edit to pause the rebase and allow you to make modifications to the files in that commit, squash to combine that commit with the one before it, or drop to delete the commit entirely. You can also physically reorder the lines in the editor to change the order in which the commits are applied. When you save and close the editor, Git executes your plan, rewiring the graph step by step. Because this rewrites history, the same warning applies. Only do this on local, unpushed commits. Mastering history manipulation in Git requires demystifying git reset. It is one of the most powerful and frequently misunderstood commands in Git. The confusion stems from the fact that it does different things depending on which flags you pass to it. Demystifying git reset starts by returning to our model of the three trees: the head pointer, the index or staging area, and the working directory. Executing git reset moves the head pointer to point to a specific commit. What happens to the other two trees depends on your flag. Running a soft reset moves the head pointer to the target commit but leaves the index and workspace untouched. Your staging area and your working directory remain completely untouched. This is extremely useful if you have made a series of small, messy commits and want to combine them into one. If you run git reset soft to a commit 3 steps back, your branch pointer moves back, but all the changes you made in those 3 commits remain staged in your index, ready for you to run git commit and create a single, clean snapshot. Opting for a mixed reset moves the head pointer and updates the staging area. leaving local files unchanged on disk. Your working directory, however, is left untouched. This means that all the changes you made since that target commit are still present on your hard drive, but they are no longer staged. They appear in your terminal as modified, unstaged files. A hard reset moves the head pointer, updates the index, and completely overwrites your working directory, discarding all uncommitted modifications. This is one of the few destructive commands in Git. Any uncommitted changes in your working directory will be lost forever, as Git will overwrite your files on disk to match the exact snapshot of the target commit. Use Git reset hard with extreme caution. We can distinguish between reset, checkout, and restore by looking at their respective scopes. While reset moves branch pointers and updates the three trees, checkout is used to switch branches by updating head to point to a different branch pointer. Modern Git has introduced the git restore command to make this cleaner. Restore is dedicated purely to discarding uncommitted changes in your working directory or staging area, leaving reset to handle pointer manipulation. When it comes to handling highly complex merge conflicts, Git offers a feature called rerear, which stands for Reuse Recorded Resolution. In large teams working with long-lived feature branches, you may find yourself repeatedly merging your branch with a shared integration branch, resolving the exact same merge conflicts over and over again. If you enable rerear in your configuration, Git will take a snapshot of the conflicting lines whenever a merge conflict occurs, and a snapshot of how you resolved it once you complete the merge. The next time Git encounters that exact same conflict anywhere in your repository, it will automatically apply your recorded resolution, saving you from manual intervention. Debugging errors in your codebase is made easier by Git Bisect, a powerful automated diagnostic tool. Imagine a bug has appeared in your system, and you know it was not there a month ago, but you have hundreds of commits between then and now. Finding the exact commit that introduced the bug manually would be tedious. Git Bisect uses a binary search algorithm to locate the offending commit. You start the process and tell Git that your current version is bad, and a specific commit from last month is good. Git then checks out a commit exactly in the middle of that history range. You run your tests or check the application and tell Git whether this middle commit is good or bad. Based on your answer, Git cuts the search space in half, checks out the next midpoint commit, and repeats the process. Within a tiny number of steps, even in a history of thousands of commits, Git Bisect will point you directly to the single commit that introduced the bug. If you need to share code across multiple projects, Git provides two main architectural approaches: submodules and subtrees. A Git submodule allows you to keep another Git repository as a subdirectory of your main repository. This is common for shared libraries or vendor code. Under the hood, a submodule is not a copy of the files. Instead, the parent repository just records a special entry in its tree pointing to a specific commit hash in the external repository, along with a .gitmodules configuration file mapping the folder path to the remote URL. When someone clones the parent repository, they must explicitly initialize and update submodules to download the external code. Because submodules are locked to a specific commit hash, they do not update automatically when the external repository moves forward, ensuring your project remains stable until you choose to update. Git subtrees offer an alternative to submodules. Instead of storing a pointer, a subtree physically imports the entire file contents of the external repository directly into your project's tree history. It allows you to track the external history and pull updates but avoids the complexity of submodules, making the repository easier to clone and manage for developers who do not need to work on the shared library directly. When you need to transfer Git data without an active network connection, Git offers a feature called bundling. Running git bundle create package name .bundle main will serialize your entire repository's history or a specific branch into a single binary file. You can copy this file to a USB drive, email it, or move it through secure offline networks. On the receiving end, developers can treat this bundle file exactly like a remote repository URL, cloning from it or pulling changes directly into their local workspaces. Git also provides a unique replacement system called Git Replace. If you have a massive repository history spanning many years, cloning can become slow due to the sheer volume of old objects. Using Git Replace, you can physically split your repository's history. You can archive the old history in a separate repository and replace the ancient commits in your active repository with empty virtual commits that have no parents. This keeps your active repository tiny and fast, while still allowing developers who need the full history to pull the replacement references and seamlessly navigate the deep past as if it were a single continuous graph. Securing your access credentials during remote network operations is handled by a credential helper system. Instead of typing your password or token every time you push or pull, Git can securely delegate credential storage to your operating system's native keychain, such as macOS Keychain or Windows Credential Manager. You can configure this using the git config command with the credential helper option, ensuring your access tokens remain encrypted at rest and are only retrieved when Git initiates a network connection. Customizing Git to enforce team policies is achieved through its highly flexible configuration system. Git configurations are split across 3 hierarchical levels: System, Global, and Local. System configurations apply to every user and every repository on your computer. They are stored in a file in your machine's global administration path, typically inside the program folder or system, etc. directory. Global configurations apply to your specific user account. They are stored in your user's home directory in a .gitconfig file. This is where you store your primary name, email, global aliases, and tool preferences. Local configurations apply only to the specific repository you are currently in. They are stored directly inside the .git/config file of your repository. Local configurations override global configurations, which in turn override system configurations. You can also use Git attributes to enforce specific file handling behaviors across different environments. Stored in a .gitAttributes file at the root of your repository, this file defines how Git treats specific file types. A common use case is managing end-of-line characters. Windows historically uses carriage return and line feed characters to end lines of text, while macOS and Linux use only line feed characters. This mismatch can lead to entire files being marked as modified just because a developer on a different operating system opened them. By defining end-of-line handling rules in your GitAttributes file, you can force Git to automatically normalize all text files to use line feeds when writing to the object database, and convert them to the operating system's native format when checking them out into the working directory. Enforcing workflows automatically is the primary role of Git Hooks. Hooks are scripts that Git executes automatically when specific events occur in the repository's lifecycle. Hooks are split into client-side hooks and server-side hooks. Client-side hooks run on your local machine. They are stored inside the .git/hooks directory of your local repository. A key example is the pre-commit hook. This script runs immediately after you run git commit, before Git even prompts you for a commit message or creates a commit object. If the pre-commit script exits with a non-zero code, Git aborts the commit entirely. Teams use pre-commit hooks to automatically run code formatters, linters, and static security analysis, ensuring that poorly formatted or insecure code can never leave a developer's machine. Other client-side hooks include the prepare commit message hook, which can dynamically inject information like the current branch name or Jira ticket number into your commit message template, and the post-commit hook, which runs after the commit succeeds and can be used for local notifications. Running on the remote server, server-side hooks are critical for enforcing corporate and team policies. The pre-receive hook runs when a client attempts to push commits to the server. Git feeds the list of references being updated to the pre-receive script. If the script rejects the push, not a single commit is accepted, and the client's push is completely aborted. This is where you enforce hard security policies, such as checking every incoming commit to ensure no developer has accidentally committed raw API keys, private certificates, or passwords. It is also where you can block force pushes to critical branches or ensure that commit messages match a strict enterprise format. The update hook behaves similarly to the pre-receive hook, but it runs once for each branch being updated, allowing for fine-grained access control on a per-branch basis. The post-receive hook runs after the server successfully updates its references. This hook cannot abort the push, but it is highly useful for triggering external automation, such as sending notifications to Slack, updating issue trackers, or kicking off continuous deployment pipelines to release the new code to staging or production. If your team is migrating to Git from a legacy version control system like Subversion, Git provides bridge tools and migration pathways. The Git SVN command allows your local Git repository to act as a client for a central Subversion server. You can fetch changes from SVN, commit locally using Git's powerful branching and merging models, and then push your changes back to the SVN server. This allows you to adopt modern Git workflows locally even if your organization is not yet ready to migrate its entire server infrastructure. When you are ready to perform a full migration, tools like Git Filter Repo are used to clean up the legacy repository during the import process. Legacy repositories often contain massive binary files or historical databases that do not belong in a Git repository. Because Git's performance relies on its object database being lean, Git Filter Repo allows you to rewrite the entire imported history graph, stripping out massive binaries, renaming folders, and correcting committer email addresses across years of history, leaving you with a clean, fast, modern Git repository. Appreciating the engineering behind Git requires peeling back the user-facing porcelain interface to explore the underlying plumbing. In Git terminology, porcelain commands are those designed for human consumption. Checkout, status, commit, branch. Plumbing commands are low-level utilities designed to manipulate the repository's internal object graph directly. In fact, almost all porcelain commands are built on top of these plumbing primitives. By learning to speak plumbing, you learn how to program Git from the inside out. Let us explore what happens in your .git folder when you run these operations. The .git directory contains several key files and folders. First, the head file. If you open this file in a text editor, you will find it contains a single line of text. In a standard repository on the main branch, it will read ref/head/main. This is Git's way of tracking your active branch pointer. Second, the config file. This is the local repository level configuration file we discussed earlier, storing your remote URLs, branch tracking configurations, and repository settings. Third, the index file. This is your binary staging area. It contains a list of every file in your project, its path, its file permissions, its modification time, and the SHA hash of the blob object representing its staged content. Fourth, the refs directory. This directory is where Git stores pointers. It contains subdirectories for heads, tags, and remotes. If you open the file ref/head/main, you will find it contains exactly one line, a 40-character hexadecimal hash. This is the exact SHA hash of the commit at the tip of your main branch. Pointers in Git are literally nothing more than text files containing commit hashes. Fifth, the objects directory. This is the heart of Git. It is the content addressable database. Inside this directory, you will find subdirectories named with 2-character hexadecimal codes, from 00 to FF. Inside these subdirectories are files with 38-character hexadecimal names. This structure is a performance optimization. If Git stored all its objects in a single flat directory, operating systems would struggle to look up files quickly as the repository grew to contain thousands of objects. By taking the first 2 characters of an object's 40-character SHA hash as the directory name, and the remaining 38 characters as the file name, Git balances the files evenly across 256 subdirectories, keeping directory lookups blisteringly fast. Let us trace how Git writes a file using plumbing commands. Imagine you have a text file containing the phrase "Hello World." If you want to write this directly to Git's database without using git add, you can use the plumbing command git hash object. You run git hash object with the right flag and pass your text file to it. Git reads the content, constructs a header consisting of the word blob, followed by a space, the size of the content in bytes, and a null byte. It prepends this header to your content, calculates the cryptographic hash of the combined data, and compresses it using zlib. It then writes the compressed data to the objects directory, using the hash as the path. The command returns the hash to your terminal. You have successfully written a blob to the database manually. Retrieving this stored content is done with another plumbing command, git catfile. If you run git catfile with the p flag, which stands for pretty print, and pass the hash, Git decompresses the object, strips off the header, and outputs your original hello world text directly to your screen. If you run catfile with the t flag, Git tells you the type of the object, which in this case is blob. Grouping these individual blobs into folders is done using tree objects. Creating a tree object through plumbing starts by updating your index file. You can do this using the command git update index. You pass the mode, which defines the file permissions, the SHA hash of the blob you just wrote, and the path you want to give to the file in your directory structure. Once your index is updated, you write it to the database as a tree object using the command git write tree. This command packages your index into a binary tree object, writes it to the objects directory, and returns its SHA hash. If you run git catfile pretty print on this new tree hash, you will see it outputs a table showing the file mode. The type is blob, the hash of your hello world blob, and the file name you assign to it. Transforming this directory tree into a formal commit is done with the git commit tree command. You pass the tree hash and tell Git which commit came before it by passing the parent flag followed by the hash of a previous commit. Git prompts you to write a commit message. When you submit, Git wraps the tree pointer, parent pointer, author, and committer metadata, and your message into a single commit object, writes it to the database, and returns the commit's SHA hash. Finally, to update your main branch to point to this new commit, you do not manually edit the ref/head/main file. Instead, you use the plumbing command git update ref. You run git update ref/head/main followed by the commit hash. Git safely locks the file, writes the hash inside it, and unlocks it. You have just performed a complete git commit using nothing but raw plumbing commands. As your repository grows, having thousands of individual loose object files on your hard drive can slow down disk operations. To keep things fast and compact, Git runs an optimization process called garbage collection or GC. When you run Git GC, or when Git triggers it automatically during common operations, Git takes all your individual loose object files and packs them into a single, highly compressed binary file called a pack file, accompanied by an index file containing byte offsets for rapid object retrieval. During this packing process, Git performs delta compression. Because codebases consist of files that are modified repeatedly, different versions of the same file share most of their content. Git looks for files with similar names and sizes, and instead of storing the entire contents of every version, it stores one full version of the file, and then stores the subsequent versions as tiny lists of differences or deltas relative to that base file. Crucially, Git is smart about how it does this. It typically stores the most recent version of the file in its entirety and stores older versions as reverse deltas. This is because you are far more likely to check out and read the latest version of a file than an ancient version, so the latest version should be readable instantly without needing to calculate and apply deltas. Managing reference synchronization between local and remote environments is handled by a system called refspecs. A refspec is a format string that defines the mapping between remote references and local references. If you look at your local repository's config file under your remote configuration, you will see a line that reads fetch equals +ref/head/asterisk:"ref/remotes/origin/asterisk." This line is a refspec. The plus sign tells Git that it should force update the references even if it is not a fast-forward merge. The left side of the colon, ref/head/asterisk, is the pattern on the remote server. The asterisk is a wildcard matching all branch names. The right side of the colon, ref/remotes/origin/asterisk, is where those branches should be written locally. This is the exact configuration that maps the remote branch named main to your local remote tracking branch named origin/main. By modifying refspecs, you can customize how Git synchronizes data, such as configuring Git to only fetch a single specific branch, or to push local tags to a different destination namespace. When Git transfers these objects over the network during fetch or push operations, it uses highly optimized transfer protocols. Modern Git uses the SMART protocol and specifically version 2 of this protocol. In version 2, the client and server engage in an intelligent negotiation. First, the server advertises its available capabilities and references. The client looks at this list and compares it to its local history graph. The client then calculates the minimal set of objects it needs. It tells the server what commits it has and what commits it wants. The server calculates the exact graph of commits, trees, and blobs that bridge the gap, packages them on the fly into a single pack stream called a multiplex pack file, and sends it to the client. This protocol is designed to minimize round trips over the network and keep packet size as small as possible. Despite Git's robust design, things can occasionally go wrong due to system crashes, power cuts, or human error. Git provides deep data recovery and maintenance systems to handle these emergencies. If you perform a hard reset to an old commit and suddenly realize you threw away critical work, do not panic. Your commits are almost certainly still in your database. Because Git never deletes objects immediately, your lost commits are still sitting inside the objects directory. They are just orphaned, meaning there are no branch pointers pointing to them. Locating these lost, unreachable commits begins with the reflog, your first line of defense. The reflog is a local ledger that records every single movement of your head pointer, regardless of why it moved. Every time you commit, check out a branch, pull, reset, or rebase, Git appends an entry to the reflog. If you run the command git reflog, Git displays this ledger, showing you a sequential list of every action you have taken, along with the SHA hash of the commit head pointed to at that moment. If you find the commit you lost, you can just run git checkout or git branch on its hash, and you will have recovered your work perfectly. If the reflog has expired, by default, Git keeps reflog entries for 90 days. You can use the database integrity tool Git FSCK, which stands for File System Check. Running Git FSCK with the -- found flag tells Git to perform a complete traversal of your history graph. It identifies every single object in your objects directory that is not reachable from any branch, tag, or reflog. It writes these dangling commits, trees, and blobs to the lost found directory inside your .git folder. You can inspect these files, find your lost code, and restore it to your active history. Finally, you can customize Git's behavior at runtime using environment variables. Git respects several key system variables that override your configuration files. For example, git_author_name and git_author_email allow you to dynamically set the identity associated with a commit on the fly, which is highly useful for automated scripting systems. Git_dir allows you to specify a different path for your repositories database, allowing you to keep your .git folder in a completely separate directory from your working tree. Git_trace can be enabled to force Git to print detailed debugging information to your terminal, showing you every internal plumbing command, config file lookup, and network packet exchange as it happens. By understanding these advanced mechanics, you move from a developer who merely uses Git to an engineer who deeply understands how to design, manage, and scale version control architectures. You see the repository not as a black box of files, but as a beautiful, immutable directed acyclic graph of project snapshots. With this mental model, you are fully equipped to build clean histories, design robust deployment pipelines, and resolve any repository crisis with complete confidence. When we transition from using Git on a single local machine to collaborating across a team or an enterprise, we must confront the mechanics of hosting Git on a server. To the uninitiated, hosting a Git server sounds like a complex task requiring heavy databases and specialized daemon processes. In reality, a Git server is elegantly simple. Because Git is fully distributed, a Git server is fundamentally nothing more than a central directory containing bare repositories, coupled with a mechanism to allow clients to read and write to those files over a network, creating a robust, scalable, and secure collaborative environment. Starts with understanding the network protocols Git uses to transfer data, how to configure a bare repository on a remote system, how to secure access using cryptographic SSH keys, and how to choose between raw command line hosting, simple web viewers, and full-featured enterprise platforms like GitLab. Analyzing how Git operates over a network requires examining the 4 primary transport protocols: local, secure shell, Git daemon, and hypertext transfer protocol. Each protocol offers distinct trade-offs in terms of setup complexity, security, transfer speed, and network compatibility. The local protocol is the most straightforward. It is used when the remote repository resides on the same physical disk or is mounted over a local area network share, such as a network file system or a server message block share. When you clone a repository using a local path, Git just reads and writes files directly from one folder to another. If you pass the directory path directly, Git attempts to use hard links to the object database on disk, which bypasses the network stack and makes the cloning process virtually instantaneous. While the local protocol is extremely fast and simple to configure, it is highly vulnerable to physical drive failures, and running Git operations over a shared network mount can suffer from severe performance degradation and file locking bottlenecks when multiple developers attempt to write simultaneously. The Secure Shell Protocol, commonly known as SSH, is the industry standard for secure, authenticated write access to a Git server. When you use SSH, you leverage the robust, enterprise-grade authentication and encryption features already built into your operating system's network stack. To Git, SSH is a highly secure tunnel. When you run a command like git push, Git initiates an SSH connection to the server, authenticates your identity using asymmetric key pairs, and then executes low-level plumbing commands on the server to stream the packed repository data over the encrypted connection. The principal advantages of SSH are that it is secure, encrypted, and universally supported by almost every server operating system. Furthermore, because SSH is a standard system utility, network administrators are highly accustomed to managing it, and it does not require running any extra, specialized services on your server. The Git daemon protocol is a dedicated, lightweight service that comes packaged directly with Git. It listens on a specific network port, 9418, and serves repositories using a highly efficient, unauthenticated transfer mechanism. When a client connects over the Git protocol, the server transfers data with virtually zero CPU overhead, making it significantly faster than SSH or HTTP. However, the Git protocol has a critical security limitation. It is entirely unauthenticated. There is no built-in way to verify the identity of the client, nor is the data stream encrypted. Consequently, the Git protocol is almost never used for write access. Instead, it is used by large open-source projects to provide lightning-fast, anonymous, read-only download access to the public. The Hypertext Transfer Protocol, or HTTP, exists in 2 distinct historical variations: Dumb HTTP and Smart HTTP. Dumb HTTP is a legacy protocol that requires no specialized Git software on the web server. It treats the Git repository as a collection of static files served from a standard web directory using servers like Apache or Nginx. When a client clones a repository over dumb HTTP, it must read the repository's internal files and download individual loose objects one by one. This results in an enormous number of HTTP requests and terrible performance, particularly for larger repositories. Smart HTTP solved these performance issues and has become one of the most popular ways to host Git. When you use Smart HTTP, the client and server negotiate data transfer dynamically. The web server acts as a proxy, passing the incoming requests to a backend CGI script called Git HTTP backend. This process dynamically packages the precise objects the client needs into a single stream, matching the speed and efficiency of SSH. Smart HTTP is highly favored because it runs over standard web ports like 80 and 443, allowing it to traverse restrictive corporate firewalls that block standard SSH and Git daemon ports. It also supports standard web authentication mechanisms, allowing teams to manage access using existing directory services. Before hosting these repositories, we must learn to set up Git on a server by initializing a bare repository. When you develop locally, your repository consists of a working directory containing your actual source code and a hidden .git directory containing the history and metadata. If you were to push changes directly to a repository that has a working directory, your push would update the repository's history, but if the server's working directory out of sync. This would create a chaotic state where the files on the server's disk do not match the latest commit history, leading to write conflicts and corrupted states. To avoid out-of-sync workspaces on remote servers, they are configured to host bare repositories. A bare repository is a repository that has no working directory. It does not contain a checkout of your source files. Instead, a bare repository contains only the files and folders that normally live inside the hidden .git directory, directly in its root folder. By convention, the directory name of a bare repository always ends with the .git extension. Initializing a bare repository on a server is done by executing git init with the --bare flag. If you inspect the contents of a newly initialized bare repository, you will see it contains several key components. The Hooks directory contains template scripts for automating tasks. The info directory contains global exclude files. The objects directory is the binary database where all your blobs, trees, and commits are stored. The refs directory holds your branch and tag pointers. The head file points to your active branch, and the config file manages repository-specific settings. Because there are no working source files, this repository exists solely to receive push operations and serve fetch requests. Securing access to this remote repository requires generating an SSH key pair on your local computer. SSH authentication relies on public key cryptography, an asymmetric encryption system where you generate two matching keys. A private key which you must keep strictly secret on your machine, and a public key which you can safely share with the world. Creating a modern, secure key pair is done using SSH keygen with the T flag to choose the algorithm. While traditional RSA keys are still widely used, the modern standard is the ED25519 algorithm, which is based on elliptic curve cryptography. ED25519 keys are exceptionally secure, have a very small key size, and offer superior performance compared to older algorithms. When you run the generator, you can secure your key with a passphrase which encrypts your private key on your hard drive, protecting it even if your computer is stolen. Once the generation process completes, your keys are stored in your home directory inside a hidden folder named .ssh. The private key is saved in a file named id_ed25519, and the public key is saved with a .pub extension. To configure the server to allow you to log in, you must read the contents of this public key file and copy its single line of text. The server uses this public key as a lock, and only your matching local private key can open it. With your public key ready, we can walk through setting up a self-hosted Git server on a Linux machine. This process represents the absolute foundation of Git systems administration. First, you log into your server and install the Git software package using the system's package manager. Once Git is installed, you should create a dedicated, unprivileged system user account named Git. This account will own all the repository files and handle all incoming SSH connections. Running Git under a dedicated user is a crucial security best practice. It ensures that even if a security vulnerability is exploited in Git, the attacker is locked inside a restricted user environment and cannot access sensitive system files or run administrative commands. Next, you switch to the Git user account and set up the SSH Authentication folder. You create a hidden directory named .ssh in the Git user's home directory and set its file permissions to 700, which ensures that only the Git user can read or write to it. Inside this folder, you create a text file named authorized_keys and set its permissions to 600. Granting a developer access to the server is done by appending their public key to the authorized keys file. When a developer attempts to connect, the server's SSH daemon reads this file and verifies that the developer possesses the matching private key. With SSH configured, you can initialize a bare repository. By convention, server administrators group all repositories in a central directory, such as srv/git. You create this folder, ensure it is owned by the Git user, and navigate inside. You then run git init with the -- flag followed by the name of your project, such as project.git. Your server is now ready to receive data. On your local development machine, you can link your existing project to the server by adding a remote. You run the command git remote add origin, followed by the SSH connection string, which consists of the Git username, the @ your server's IP address or domain name, a colon, and the absolute path to your bare repository, such as srv/git/project.git. Running git push with the upstream flag set to origin main prompts your local client to initiate the SSH handshake, log in, stream the data, and update the branch pointer. While this setup works perfectly, it introduces a significant security vulnerability. By default, any user whose key is in the authorized_keys file can log into the server over SSH and get a full interactive bash shell. This means they could run arbitrary commands, explore your server's file system, or even delete files. Securing this potential vulnerability is handled by Git Shell, a restricted login shell. Git Shell is a specialized shell program that does not allow interactive terminal commands. Instead, it only allows the user to run the specific plumbing commands that Git uses to push and pull data, such as git receive pack and git upload pack. Implementing this safety measure involves changing the Git user's login shell to Git shell inside the server password file. Once configured, if a user attempts to log into the server over SSH manually, they will see a polite rejection message indicating that interactive access is closed, but their local Git client will still be able to push and pull data seamlessly. If you are hosting open source code and want to provide fast, anonymous, read-only access to the general public, you can configure the Git daemon. Setting up the Git daemon involves running a system service that listens on port 9418. Securing a Git daemon setup requires running the service under a restricted read-only account, scoped to a specific directory path. By default, the Git daemon will not serve any repository unless you explicitly allow it. To export a repository for public access, you must create an empty Sentinel file named Git daemon export OK inside the repository's bare directory. When an external user requests a clone using the git // protocol, the daemon checks for this file. If it is present, The daemon streams the repository objects using the raw TCP connection, offering unmatched read performance without the overhead of encryption or user authentication. For organizations that cannot open port 22 for SSH or port 9418 for the Git daemon, Smart HTTP is the ultimate solution. Setting up Smart HTTP requires configuring a web server like Apache or Nginx to handle incoming Git requests and route them to Git HTTP backend. Git HTTP backend is a highly optimized CGI program that is installed alongside Git. It reads environment variables passed by the web server, such as the request path and query parameters, to determine what action the client is trying to perform. When a client initiates a fetch or a push, the web server handles the SSL encryption and manages user authentication, which can be hooked into a standard Active Directory or LDAP server. Once authenticated, the web server pipes the incoming data stream to Git HTTP backend, which processes the objects and updates the bare repository directly on the server's disk. This allows teams to collaborate securely using standard web technologies. While a raw Git server is powerful, developers often struggle to inspect repository histories, view commit messages, or perform code reviews solely from the command line. To solve this, you can configure Git Web, a lightweight web interface that comes built in with Git. Git Web is a simple CGI script written in Perl. When configured on your web server, Git Web reads your bare repositories directly from the disk and renders a clean, retro-style HTML interface. Through this web page, developers can browse the folder structure of any branch, view detailed commit messages, inspect visual diffs of changes, and track the project's branch history graph. Git Web requires almost no system resources and does not run any heavy background processes, making it a perfect tool for small teams or private servers that need a simple, visual index of their code without the overhead of a full management platform. As teams scale, they eventually outgrow raw servers and simple web viewers. They require advanced code review pipelines, issue tracking, continuous integration, and deep authorization controls. This is where GitLab shines. GitLab is a complete, self-hosted DevSecOps platform that manages the entire software development lifecycle. Under the hood, GitLab's architecture is a highly engineered system designed to handle thousands of concurrent developers and petabytes of Git data. At its core, GitLab consists of several decoupled components. The web interface and primary business logic are powered by a Ruby on Rails application. However, because executing Git commands directly inside a web application is slow and memory-intensive, GitLab does not access Git repositories using raw disk operations. Instead, GitLab routes all Git operations through a highly optimized, Go-based service called Gitali. Gitali is a gRPC-based service that runs directly on the storage servers hosting your bare repositories. When a developer pushes code, views a diff in the browser, or merges a pull request, the GitLab web application sends a structured gRPC call to Gitali. Gitali then executes the highly optimized Git plumbing commands locally on the storage node, formats the output, and streams the results back to the web application over a high-speed network socket. This architecture decouples the web application from the physical storage layer, allowing organizations to scale their Git storage nodes independently from their web servers. GitLab also features a highly scalable automated execution engine called GitLab Runner. Runners are lightweight agents that run on separate build servers, virtual machines, or Kubernetes clusters. When code is pushed to a repository, GitLab coordinates with these runners to execute continuous integration and continuous deployment pipelines, automatically compiling code, running testing suites, scanning for security vulnerabilities, and deploying containers to production environments. This tight integration of Git storage, code review, and automated execution is what makes self-hosted platforms like GitLab the backbone of modern enterprise software engineering. For teams that do not want to manage their own hardware, maintain security patches, or administer servers, third-party hosted options, or software-as-a-service platforms dominate the industry. The most prominent SaaS providers are GitHub, GitLab SaaS, and Atlassian Bitbucket. When you use a third-party hosted option, you outsource the operational complexity of hosting Git. These platforms operate massive, globally distributed infrastructure networks that guarantee high availability, automatic data replication, and robust security compliance. They provide rich, web-based code review interfaces, integrate with popular project management tools, and support extensive marketplace ecosystems that allow you to extend your workflow with automated bots and third-party integrations. However, choosing between a self-hosted server and a third-party hosted platform involves critical architectural trade-offs. Self-hosting gives you complete, absolute sovereignty over your code. This is a strict requirement for financial institutions, government agencies, and healthcare companies that must comply with strict regulatory frameworks. When you host your own Git server, your source code, which is your company's most valuable intellectual property, never leaves your private network. You have total control over backup strategies, security configurations, and update cycles. On the other hand, self-hosting requires significant operational overhead. Your engineering team must spend valuable time patching operating systems, configuring firewalls, managing storage capacities, and troubleshooting network outages. Third-party hosted options eliminate this operational burden completely. Your team can focus entirely on writing software, confident that the hosting provider's dedicated infrastructure teams are managing backups, scale, and server security. Yet, this convenience introduces external dependencies. You are subject to the provider's pricing structures, service-level agreements, and potential network outages. For many modern startups and agile teams, the speed, ease of use, and rich collaborative ecosystems of SaaS platforms far outweigh the architectural control of running a private server. By mastering these server architectures, from the underlying network protocols and SSH key management to self-hosted Git shell environments, smart HTTP proxies, and enterprise platforms like GitLab, you gain the system design knowledge required to build a secure, performant, and resilient collaboration infrastructure that perfectly matches your organization's security posture and scaling requirements. Appreciating the full scope of Git means looking beyond local execution to examine its capabilities as a distributed collaboration engine. Because Git is fully distributed, every developer has a complete copy of the entire project history on their machine. This design eliminates the dependency on a single central server for daily operations, allowing developers to commit, branch, and view history completely offline. However, this distributed architecture also introduces unique challenges. How do teams synchronize their work without overwriting each other's changes? How do project maintainers review, integrate, and verify contributions from hundreds of disparate developers? By mastering distributed workflows and understanding how platforms like GitHub implement these patterns at scale, you can design highly efficient, secure, and collaborative software delivery pipelines. Let us first examine the different distributed workflows that teams can adopt. The choice of workflow dictates how developers communicate, how code is reviewed, and how changes are ultimately integrated into the master codebase. The first model is the centralized workflow. In this model, there is a single central repository, often called the Golden Repository, and every developer on the team has direct push access to it. Developers pull the latest changes, make their commits locally, and then attempt to push them back to the server. If another developer has pushed changes in the meantime, the push is rejected. The developer must then fetch the remote changes, merge or rebase their local work on top of those changes, and attempt to push again. This workflow is popular among teams transitioning from legacy centralized systems because it mimics their old patterns. While simple, it does not scale well for large teams, as developers frequently run into push races, where they must constantly pull and merge before they can share their work. Scaling collaboration beyond push races is typically done with the Integration Manager workflow. In this workflow, there is an official read-only repository, often referred to as the upstream repository, and a single integration manager who has write access to it. Developers do not have write access to upstream. Instead, they create a personal copy of the upstream repository on the server, which is known as a fork. Developers clone their personal fork to their local machine, perform their work, and push their changes back to their personal remote fork. To integrate their work into the official project, the developer sends a request, known as a pull request or merge request, to the integration manager. The integration manager reviews the changes, requests modifications if necessary, and eventually pulls the changes from the developer's public fork and merges them into the official upstream repository. This model is exceptionally popular for open-source projects and large corporate codebases because it keeps the production branches highly protected and ensures that every change undergoes rigorous review before integration. For massive, globally distributed projects like the Linux kernel, a hierarchical model known as the dictator and lieutenants workflow is used. In this model, there is a single benevolent dictator who maintains the official main repository. Beneath the dictator are several lieutenants, who are trusted maintainers in charge of specific subsystems of the codebase, such as file systems, network drivers, or security. Ordinary contributors write code and submit their changes to the lieutenant in charge of the relevant subsystem. The lieutenant reviews and merges these changes into their own subsystem branch. Once the subsystem is stable, the lieutenant sends a merge request to the dictator. The dictator then pulls the approved branches from all the lieutenants and merges them into the official master repository. This hierarchical design prevents any single individual from becoming a bottleneck, distributing the heavy burden of code review across a trusted network of subsystem specialists. Regardless of the workflow your team chooses, contributing to a project requires a disciplined approach to preparing, structuring, and describing your changes. When you contribute to a project, your goal is to make the maintainer's job as easy as possible. A well-prepared contribution is clean, highly cohesive, and thoroughly documented. The foundation of a good contribution is a clean commit history. When you are developing a feature locally, you might make many small, messy commits with messages like fix, typo, or test. While this is fine for local experimentation, you should never share this messy history with a project maintainer. Before submitting your work, you should use interactive rebasing to clean up your commit history. You should squash minor fix commits, delete redundant changes, and reorder commits so they present a logical, step-by-step progression of your feature. Each commit in your history should represent a single, self-contained, working snapshot of the system. Each commit should compile, pass all testing suites, and contain only related modifications. Equally important are the commit messages you write. A commit message is the primary historical documentation for your codebase. It should not merely describe what changed, as Git can already show you the exact file differences. Instead, a commit message should explain why the change was made, what problem it solves, and what side effects the maintainer should be aware of. Maintaining commit message consistency across global teams is achieved through industry-standardized formats. A professional commit message begins with a short, 50-character subject line. This line should be written in the imperative mood, as if you are giving a command to the codebase. For example, you should write add user authentication module rather than added user authentication module or adds user authentication module. This matches the tense Git itself uses when it generates automatic merge messages. After the subject line, you must leave a blank line followed by a detailed body. The body should be wrapped at 72 characters to ensure it renders beautifully in standard terminal viewers. In this body, you explain the context of the change, the technical approach you took, and any trade-offs you encountered. If your change fixes an issue, you should explicitly reference the issue number, which allows hosting platforms to automatically link and close the issue when the commit is merged. Once your commits are clean, you can share them. If you are working on a project where you do not have direct write access or a web-based platform, you can share your changes by generating raw patch files. Git provides a specialized command called Git format patch. This command takes a range of commits and converts each one into an individual email-friendly text file containing the diff, the commit metadata, the author's name, and the commit message. You can then use the command git send email to stream these patches directly to a project mailing list. This allows maintainers to review your work entirely through their email clients. When you transition from a contributor to a project maintainer, your responsibilities shift. As a maintainer, you are the gatekeeper of the project's quality, stability, and historical integrity. You must review incoming changes, verify their quality, and integrate them into the master history graph. When a contributor sends you a patch or a pull request, you must first inspect and test their code in a safe, isolated environment. If you received raw patches via email, you can use the command git apply to apply the changes directly to your working directory. However, Git apply only modifies your files on disk. It does not preserve the author's commit messages or metadata. Preserving the complete metadata and author history is done via the git m command. This command parses the patch files, applies the file modifications, and automatically creates corresponding commit objects in your history, preserving the contributor's authorship, date, and commit messages. If the contribution contains errors, you should not edit their commits directly. Instead, you should communicate with the contributor, request modifications, and have them update their branch. This preserves clear accountability and respects the contributor's authorship. Once you are satisfied with the changes, you must choose how to integrate them into your main branch. As a maintainer, you have three primary integration strategies: merge commits, squashing, and rebasing. A standard merge commit takes the contributor's branch and performs a three-way merge, creating a new merge commit with two parent pointers. This preserves the complete, unaltered history of how the feature was developed. including every intermediate commit the contributor made. While historically accurate, this can lead to a highly complex, nonlinear history graph if many developers are working in parallel. Alternatively, you can choose to squash the contribution. Squashing takes all the commits on the contributor's branch and condenses them into a single, unified commit on your main branch. This keeps your history extremely clean and linear, but it throws away the granular step-by-step history of how the feature was built. The third option is to rebase and merge. This strategy takes the contributor's commits, reapplies them one by one on top of your main branch, and then performs a fast-forward merge. This maintains a completely linear history while preserving individual, cleaned-up commits. As a maintainer, you must choose the strategy that best matches your organization's architectural guidelines and history retention policies. At scale, the software industry relies heavily on GitHub to orchestrate distributed workflows. GitHub is not just a hosting provider. It is a massive collaborative platform that standardizes and enhances raw Git mechanics. Collaborating on GitHub starts with setting up your user profile and security credentials. Beyond creating a user profile, you must establish secure authentication mechanisms. GitHub strictly enforces secure access, requiring developers to authenticate using SSH keys or personal access tokens rather than standard passwords. When you generate an SSH key locally and add the public key to your GitHub account settings, GitHub uses this key to authenticate your Git push and Git pull operations over SSH. For command line operations over HTTPS, you must generate a personal access token, which behaves like a highly restricted, scoped password that you can revoke at any time. Attributing your local commits to your GitHub profile requires configuring your local Git name and email to match your GitHub account. You run the commands git config global user.name and git config global user.email. If your local email address matches the email registered in your GitHub account, GitHub will automatically associate your pushed commits with your user profile, rendering your avatar and linking your name directly to your profile. Once configured, contributing to a project on GitHub follows a highly structured visual workflow. You begin by navigating to the target project's repository on GitHub and clicking the fork button. This creates an exact copy of the repository under your personal GitHub account. Next, you clone your personal fork to your local computer. This cloned repository has a single remote named origin, which points to your fork on GitHub. To keep your local repository up to date with the original project as other developers make changes, you should add a second remote pointing to the original repository. By convention, this second remote is named upstream. You run the command git remote add upstream, followed by the URL of the original project. Beginning your actual task starts with creating a new local feature branch. You make your modifications, clean up your commits using interactive rebasing, and push your branch back to your personal fork on GitHub. Pushing a branch to GitHub triggers a web notification presenting a button to open a pull request. A pull request is a rich collaborative document. It allows you to write a detailed markdown description of your changes, link to issues, request reviews from specific team members, and attach images or videos. Opening the pull request triggers automated continuous integration suites to compile and test your changes. These systems pull your code, compile it, and run your testing suites, displaying a pass or fail badge directly inside the pull request interface. Peer reviewers can inspect your changes line by line, write comments directly on specific lines of code, and suggest modifications that you can apply with a single click. If the maintainer requests changes, you just make the edits on your local machine, commit them, and push them back to your branch on your fork. GitHub automatically updates the pull request with your new commits, keeping the entire conversation and code progression in one central place. When you are the maintainer of a project on GitHub, you use the platform's advanced administrative features to protect the stability and security of your codebase. Your primary tool for protecting your code is branch protection rules. Through your repository settings, you can define rules for your production branches, such as main or release. You can configure GitHub to completely block any developer from pushing code directly to these branches, requiring all changes to go through a pull request. You can also enforce policies that require pull requests to receive a specific number of peer approvals, pass all automated status checks and testing suites, and maintain up-to-date linear histories before they are allowed to merge. This ensures that no broken or unreviewed code can ever enter your production branches. GitHub also provides sophisticated project management tools directly integrated with your code. You can use issues to track bugs, feature requests, and tasks. You can organize these issues on visual project boards, which behave like digital Kanban boards, allowing you to drag and drop tasks between columns like backlog, in progress, and completed. By linking issues directly to pull requests, you can configure GitHub to automatically close the corresponding issue as soon as the pull request is merged into the main branch. As organizations grow, they must manage collaboration across many teams and repositories. GitHub provides the organization structure to meet this enterprise need. An organization is a shared account that acts as a container for all your company's repositories, projects, and users. Within an organization, you can group users into teams. Teams can reflect your company's physical engineering structure, such as the front-end team, the security team, or the platform engineering team. You can assign fine-grained access permissions to these teams at the organization or repository level. Instead of configuring access permissions for individual developers one by one, you assign permissions to the team. For example, you can give the platform team write access to your deployment configurations, the QA team read-only access to the source code, and the core engineering team admin access to the repository settings. Organizations also provide advanced security and administrative controls. You can enforce single sign-on using corporate directory services like Active Directory or Okta, ensuring that when an employee leaves your company, their access to your source code is instantly revoked. You can also enable advanced security tools like secret scanning, which continuously scans every single pushed commit for raw API keys, private certificates, or database passwords, instantly alerting your security team and blocking the leak. Additionally, tools like Dependabot automatically scan your project's dependencies for known security vulnerabilities, generating automated pull requests to upgrade your libraries to safe versions without manual intervention. To scale these workflows, modern DevOps teams must automate their interactions with GitHub. GitHub provides robust scripting capabilities through its command line tool, its REST API, and its GraphQL API. The GitHub command line interface, known as GH, allows you to interact with GitHub's rich platform features directly from your terminal. Instead of opening a web browser to manage your work, you can run commands to create repositories, clone forks, view issues, and open pull requests. For example, to view all open issues assigned to you in the current project, you just run GH issue list. To view the review status of your current pull request, you run GH PR status. This command line integration allows you to build highly personalized shell scripts that automate your daily developer workflows. For deep, custom integrations and automation platforms, GitHub provides a comprehensive REST API and a highly optimized GraphQL API. The REST API is a standard HTTP interface that exposes individual resources like users, repositories, commits, and issues through specific URL endpoints. For example, to retrieve a list of all repositories in an organization, your automation script sends an authenticated GET request to the organization's repositories endpoint. The server processes the request and returns a JSON payload containing the repository details. However, as codebases and teams grow, using the REST API can lead to performance bottlenecks. If your script needs to find the review status of every pull request in a repository, and also retrieve the avatar images of the reviewers, it must make a request to get the pull requests, and then make a separate network request for each individual user to get their avatar. This is known as the N+1 query problem, and it results in an enormous number of network round trips. Resolving the N+1 query bottleneck is the primary goal of GitHub's GraphQL API. GraphQL is a query language for your API that allows you to define the exact shape of the data you want. Instead of making multiple requests to different URL endpoints and receiving massive, nested JSON payloads with unneeded information, you make a single post request containing a structured query. In this GraphQL query, you define your entry point, such as the repository, and specify the exact fields you need, such as the pull request titles, their merge status, and the specific names and avatar URLs of their reviewers. The GitHub API server parses this query, executes a single, highly optimized database lookup, and returns a single JSON payload containing only the exact fields you requested. This dramatically reduces network payload sizes, eliminates overfetching, and allows you to write lightning-fast automation scripts that can monitor, audit, and orchestrate thousands of repositories across a global enterprise. By mastering these distributed collaboration mechanics, from the architectural patterns of forked workflows and integration managers, to the discipline of clean commit history, robust branch protection policies, organizational team structures, and advanced GraphQL API scripting, you elevate your engineering capability. You transform from a developer who writes code in isolation to an enterprise architect who can design, automate, and scale secure software delivery pipelines across global engineering organizations. True mastery of Git requires looking beyond basic workflows to explore its advanced data manipulation and diagnostic tools. Git is not just a version control tool. It is a highly sophisticated data manipulation and diagnostic engine. As code bases grow, histories become complex, and development teams scale, you will inevitably encounter scenarios that require precise history rewriting, deep search capabilities, automated debugging, and complex dependency management. By mastering Git's advanced tools, you can navigate massive repositories with ease, recover lost work, automate bug hunting, and maintain a pristine code base under any circumstances. Operating at this advanced level begins with mastering revision selection. When you run a command that acts on a commit, you do not have to copy and paste the 40-character SHA-1 or SHA-256 hash. Git provides several elegant ways to reference specific commits or ranges of commits in your history graph. The simplest way is using a short SHA. Git only needs enough characters of a hash to make it unique within the repository's database. While the minimum is 4 characters, Git defaults to 7 or 8 characters in most output. In massive repositories, you may need a few more characters to avoid hash collisions. You can also use human-readable references, such as branch names, tag names, or the special head pointer, which points to your current checkout. However, the true power of revision selection lies in ancestry references. Git provides two distinct symbols for traversing backward through the history graph: the caret symbol and the tilde symbol. Understanding the difference between these two symbols is critical, especially when working with nonlinear merge histories. The caret symbol, written as a commit reference followed by a caret, refers to the parent of that commit. If you are looking at a standard commit with only one parent, writing head caret refers to that parent. However, if you are looking at a merge commit which has multiple parents, the caret symbol allows you to specify which parent line you want to follow. Writing head caret 1 refers to the first parent, which is the branch you were on when you executed the merge. Writing head caret 2 refers to the second parent, which is the branch that was merged in. If a commit has 3 parents, which is known as an octopus merge, writing head caret 3 refers to the third parent. The tilde symbol, written as a commit reference followed by a tilde, refers to a straight line ancestor. When you append a number to the tilde, such as head tilde 3, you are telling Git to go straight back that many generations, always following the first parent of any merge commits it encounters. It is a shortcut for writing head caret 1 caret 1 caret 1. Visualizing this ancestry difference is easier when you think of a family tree. Caret 1 is your mother, caret 2 is your father. Tilde 2 is your maternal grandmother, because you went back 2 generations always following the first parent line. In addition to referencing single commits, you will frequently need to specify ranges of commits. This is highly useful for viewing logs, generating patches, or comparing branches. Git provides 2 primary range operators: the double dot and the triple dot. The double dot operator, written as commit A double dot commit B, resolves to all commits reachable from commit B that are not reachable from commit A. Imagine you have a feature branch that you diverged from your main branch. If you run git log main double dot feature, Git will show you only the commits you have made on your feature branch since you diverged. It completely filters out all commits that are already present in the main branch's history. The triple dot operator, written as commit A triple dot commit B, resolves to all commits that are reachable from either commit A or commit B, but not from both. This is known in mathematics as the symmetric difference. When you run git log with the triple dot operator, Git shows you all the unique commits on both branches since their common ancestor, but hides the commits they share. If you add the double dash left-right flag to this command, Git will prepend a left or right angle bracket to each commit in the log, showing you exactly which branch each commit belongs to, making branch comparisons extremely clear. Once you have selected your revisions, you often need to prepare your changes for a commit. While we typically stage entire files using git add, Git provides an interactive staging system that allows you to construct highly precise commits. By running the command git add with the double dash interactive flag or the shortcut double dash patch flag, you enter a guided command line interface. In patch mode, Git reads the modifications in your working directory and breaks them down into individual units of change called hunks. Git displays each hunk to you one by one, highlighting the added and deleted lines, and prompts you with a list of actions. You can press the Y key to stage the hunk, or the N key to keep it unstaged. If a hunk contains multiple unrelated edits, you can press the S key to split it into even smaller hunks. If Git cannot split the changes automatically because they are on adjacent lines, you can press the E key to manually edit the hunk in your text editor. This allows you to delete individual lines of code from the staging blueprint, ensuring your next commit contains only the exact changes you want to release, even if your working directory is filled with temporary debugging code or unrelated edits. If you are in the middle of a complex change and must suddenly switch branches to handle an urgent issue, you cannot do so if your uncommitted changes would be overwritten. To handle this common scenario without losing your progress, Git provides stashing and cleaning. Running git stash saves all modified, tracked files to a temporary stack and cleans the workspace. It then resets your working directory and staging area to match the head commit, leaving you with a pristine workspace. Under the hood, Git Stash performs a fascinating set of operations. It does not just copy files to a backup folder. Instead, it creates a set of temporary commit objects on a special reference called ref/stash. It creates one commit to represent the state of your staging area and a second commit to represent the state of your working directory. Because these are real commits in your Git database, your changes are safely stored and protected from accidental deletion. By default, Git Stash only saves modified, tracked files. If you have newly created, untracked files in your working directory, they will be left behind. To stash these files as well, you must run git stash with the -- include untracked flag. If you need to stash absolutely everything, including files that are explicitly ignored by your .gitignore file, you can use the -- flag. When you return to your feature branch, you can run git stash apply to restore your changes, or git stash pop, which restores your changes and simultaneously deletes them from the stash stack. If you want to test your stash changes in isolation, you can run git stash branch followed by a new branch name. This command creates a new branch at the commit you were on when you stashed, restores your changes to the working directory, and deletes the stash from your stack, preventing any merge conflicts. If you need to completely discard untracked files instead of saving them, you use git clean. Running git clean with the -- force flag will permanently delete all untracked files from your working directory. Avoiding accidental file deletion is done by running git clean with the dry run flag first. This tells Git to print a list of the files it would delete without actually performing the operation. If you want to delete untracked folders as well, you must pass the D flag, and to delete ignored files, you pass the X flag. For security-conscious environments, Git supports cryptographically signing your work. When you commit, anyone can configure their local Git config file to use your name and email address, allowing them to easily spoof your identity in the repository's history. Protecting your commits from identity spoofing is achieved by signing them with cryptographic keys. When you configure Git to use your signing key and run a commit command with the S flag, Git hashes the commit's metadata and writes a cryptographic signature directly into the commit object itself. When other developers or hosting platforms pull your commits, they can use your public key to verify that the signature is valid. This guarantees that the commit was genuinely written by you and has not been modified since its creation. As your repository grows to contain thousands of files and millions of lines of code, finding specific pieces of information becomes a challenge. Git provides extremely fast, powerful search tools that operate entirely offline. The command git grep allows you to search for specific strings or regular expressions across your entire project. Unlike standard terminal search tools like grep or find, Git grep is designed specifically for Git. It ignores files that are untracked or listed in your .gitignore file, preventing your search results from being cluttered with build artifacts or dependency folders. Furthermore, because it reads directly from the Git index, it is exceptionally fast. You can use Git grep to search your current working directory, or pass a commit reference to search what your codebase looked like at any point in the past. If you need to search your commit history rather than the code itself, you use git log with the uppercase S flag, which is known as the pickaxe option. When you run git log with the pickaxe option followed by a search string, Git does not just search for that string in commit messages. Instead, it scans the file differences of every commit in your history and shows you only the commits where the number of occurrences of that string changed. This is extremely useful for finding the exact commit where a specific function, variable, or error code was first introduced or deleted from your codebase. If you need to search using regular expressions across your file history, you can use git log with the uppercase G flag. For even more granular code tracing, you can use the uppercase L flag, which is the line log search. This command takes a line range or a function name and a file name, such as git log L : function name : file name. Git will then scan your history and output a dedicated log showing the complete evolution of only that specific function over time, filtering out all other changes in the file. Eventually, you will need to modify your repository's history. Whether you need to fix a typo in an old commit message, combine a series of small commits before a release, or completely remove a sensitive file that was accidentally committed, Git provides robust history rewriting capabilities. For simple, immediate changes, you use git commit with the ~amend flag. This command takes whatever you currently have staged in your index, combines it with the parent pointers and metadata of your very last commit, and writes a brand new commit object to the database, replacing the old one. For deeper history modifications, you use interactive rebasing. By running git rebase with the interactive flag and specifying a parent commit, such as git rebase interactive head~5, Git opens a list of the last 5 commits in a temporary text editor. This list is a sequential recipe of commands. Each commit is prefixed with the word pick. To rewrite history, you change these commands. You can change pick to reword to modify a commit message, edit to pause the rebase at that commit and allow you to edit files or stage changes, squash to combine that commit's changes and message with the commit before it, or fix up to combine the changes but discard the message. You can also physically reorder the lines in the editor to change the chronological order in which the commits are applied, or delete a line entirely to delete that commit from history. When you save and close the editor, Git executes your recipe step by step. If it encounters a conflict, it pauses, allows you to resolve it, and continues. Because this process changes parent pointers, it generates entirely new commit hashes for all subsequent commits. Therefore, the same golden rule applies. Only rewrite local, unpushed history to avoid disrupting other developers. If you need to perform a massive, automated rewrite of your entire repository, such as stripping a large database file from every single commit in your history, you should not use interactive rebasing. Instead, you use specialized tools like Git Filter Repo. Git Filter Repo is a modern, high-performance Python script that replaces the legacy Git filter branch command. It allows you to write complex filters to rewrite your entire history graph in seconds. You can use it to rename folders across all historical commits, extract a subdirectory into a new independent repository while preserving its history, or completely purge sensitive passwords and files from your entire commit history. Demystifying Git reset is a prerequisite for mastering history rewriting and database recovery. It is one of the most powerful and feared commands in Git, but its behavior is completely logical when understood through the lens of the 3 trees. the head pointer, the index, and the working directory. When you run git reset, you are telling Git to move the current branch pointer to point to a specific commit hash. What happens to your staging area and your working directory depends entirely on the flags you pass: soft, mixed, or hard. To understand the difference, let us trace a scenario. Imagine you have a branch where your main branch points to commit A, and you have made two commits, B and C. Your head currently points to commit C. Invoking a soft reset back to commit A moves the pointer without touching index or files. It does not touch your staging area or your working directory. This means that all the changes you made in commits B and C are still completely present on your hard drive, and they are still staged in your index. If you run git status, you will see all these changes marked as staged and ready to commit. Soft reset is a non-destructive way to undo commits and group their changes together. Executing a mixed reset moves the head pointer and updates the staging index, leaving local files intact. First, it moves your branch pointer and head back to commit A. Second, it updates your staging area to match commit A. Your working directory, however, is left completely untouched. The changes you made in commits B and C are still on your hard drive, but they are no longer staged. If you run git status, you will see these files marked as modified but unstaged. A hard reset moves the head pointer, updates the index, and completely overwrites local files. It moves head to commit A, updates your staging area to match commit A, and completely overwrites your working directory to match commit A. Any uncommitted changes on your hard drive are instantly lost, and your files are reverted to the exact state they were in at commit A. Hard reset is a highly destructive operation, as Git completely overwrites your local workspace. We can distinguish between reset, checkout, and restore by looking at their safety guarantees and operational scopes. While reset moves branch pointers, checkout is used to switch branches by updating head to point to a different branch reference. Checkout is safe. It will prevent you from switching branches if you have uncommitted changes that would be lost. Restore is a modern command dedicated purely to reverting files in your working directory or staging area without moving any pointers. As you collaborate on complex histories, you will eventually face advanced merging scenarios. While Git handles most merges automatically, you must occasionally manage complex conflicts and merge failures. When a merge conflict occurs, Git pauses and enters a conflicted state. You can run git status to view a list of conflicted files. Resolving conflicts by picking one version entirely can be done using git checkout with the hours or there's flags. The hours flag tells Git to keep the version from your current branch, while the there's flag tells Git to keep the version from the branch you are merging in. If you want to view the common ancestor of the conflicting files to understand why they diverged, you can configure your conflict style to diff3. In this style, Git's conflict markers will display three sections: the changes on your branch, the code as it existed in the common ancestor, and the changes on the incoming branch. This gives you complete context for manual resolution. Undoing a merge commit that introduced a critical regression is possible using git revert. However, reverting a merge commit is complex because a merge commit has two parents. When you run git revert on a merge commit, you must pass the M flag followed by a number to specify which parent line should be kept as the main history. For example, git revert M1 tells Git to revert the changes introduced by the merge, keeping the history of your first parent branch intact. To avoid repeatedly resolving the same merge conflicts when working with long-lived feature branches, you can enable rerear, which stands for Reuse Recorded Resolution. When you enable rerear in your global configuration, Git keeps a local database of your conflict resolutions inside the .git/rr cache directory. When a merge conflict occurs, rerear takes a digital fingerprint of the conflicting lines of code. Once you manually resolve the conflict and commit the merge, rerear records your exact resolution. If Git encounters that exact same conflict anywhere in your repository in the future, it automatically applies your recorded resolution, saving you from manual intervention. When bugs inevitably slip into your codebase, Git provides powerful debugging tools to help you identify the root cause of the failure. The first of these is git blame. When you run git blame followed by a file name, Git displays the file line by line, prepending each line of code with the SHA hash of the commit that last modified it, the author's name, and the timestamp. This allows you to instantly trace the authorship and context of any line of code. If code has been moved from one file to another, a standard blame command might attribute the line to the commit that moved it, rather than the commit that actually wrote it. To solve this, you can run git blame with the C flag. This tells Git to analyze other files in the commit history and detect if lines of code were copied or moved. Git will then bypass the copy commit and attribute the authorship to the genuine creator, even if the code now lives in an entirely different file. For automated bug hunting, you use Git Bisect. Imagine a bug has appeared in your application, and you know it was not there a month ago, but you have hundreds of commits between then and now. To start, you run git bisect start. You tell Git that your current version is bad by running git bisect bad, and your version from a month ago is good by running git bisect good followed by that old commit hash. Git then calculates the midpoint of this history range and automatically checks out that commit. You run your application and test for the bug. If the bug is present, you type git bisect bad. If the bug is absent, you type git bisect good. Based on your input, Git performs a binary search, cutting the remaining search space in half each time, and checks out the next midpoint. Within a tiny number of steps, Git Bisect will point you directly to the single commit that introduced the bug. If you can write a test script that exits with a code of 0 if the code is good, and a code of 1 if the code is bad, you can completely automate this process. You just run the command git bisect run followed by the path to your script. Git will execute the binary search, run your script at each step, and find the offending commit in seconds without any manual intervention. As your projects scale, you will often need to manage code dependencies across multiple repositories. Git provides two distinct tools for this: submodules and subtrees. A Git submodule allows you to embed another Git repository as a subdirectory of your main repository. This is highly useful for shared libraries or vendor code. When you add a submodule, Git does not copy the external repository's files into your project's history. Instead, the parent repository just records a special entry in its tree history with the file mode 160000, which is known as a Git link. This Git link points directly to a specific commit hash in the external repository. It also creates a .gitmodules configuration file at the root of your project, which maps the folder path to the remote URL of the submodule. When another developer clones your repository, they must run git submodule init and git submodule update to download the submodules files. Because submodules are locked to a specific commit hash, they remain completely stable until you explicitly choose to update them, preventing upstream changes from breaking your application. Git subtrees offer an alternative dependency model. Instead of storing a pointer, a subtree physically imports the entire file history and contents of the external repository directly into your project's tree. It allows you to pull updates and even push modifications back to the external repository, but avoids the administrative complexity of submodules, making the repository easier to clone and manage for developers who do not need to work on the shared library directly. For situations where you must transfer repository data over air-gapped networks, physical media, or secure email channels, Git provides bundling. By running git bundle create followed by a file name and a branch name, Git serializes your entire repository's history or a specific branch range into a single, highly compressed binary file. You can copy this file to a USB drive or send it across networks. On the receiving machine, developers can run git clone directly on the bundle file as if it were a remote repository URL, allowing for full distributed collaboration without any network servers. If you have an ancient, massive repository history that makes cloning slow, you can use git replace to archive the past. Using git replace, you can physically split your repository's history. You can extract your old history into an archive repository and replace the ancient commits in your active repository with empty virtual commits that have no parent pointers. This keeps your daily development repository tiny, fast, and light. If a developer needs to debug deep historical code, they can just fetch the replacement references from the archive, and Git will seamlessly stitch the history back together on the fly. Securing your access credentials during remote operations is handled by native credential helpers. Instead of typing your SSH passphrase or HTTPS personal access token every time you push or pull, you can configure Git to securely store and retrieve your credentials. Git provides several credential storage strategies. The cache helper stores your credentials in your computer's temporary system memory for a set number of minutes, which is highly secure as they are never written to disk. The store helper writes your credentials in plain text to a file on your hard drive, which is simple but highly insecure. For enterprise-grade security, you should use your operating system's native secure keychain helper, such as OSCSkychain on macOS or Winkard on Windows. These helpers encrypt your access tokens and store them within your operating system's secure keychain, ensuring they are only retrieved when Git initiates an authenticated network connection, balancing seamless convenience with robust security. By mastering this advanced toolset, from precise revision selection and interactive staging to history rewriting, deep search indexers, automated binary debugging, and secure cryptographic signing, you elevate your engineering capability. You are no longer just a user of version control. You are a master of repository architecture, fully equipped to manage, secure, and debug the most complex code bases in the software industry. One of the greatest strengths of Git is its deep customizability. Git is not a rigid, opinionated tool. It is a flexible framework that you can tailor to your exact development workflows, code formatting standards, security requirements, and team policies. By mastering Git's configuration system, file attributes, client-side and server-side hooks, and migration pathways, you can transform Git from a basic version control utility into a highly customized, automated system that actively enforces software quality and integrates seamlessly with any legacy platform. Customizing Git begins with mastering its hierarchical configuration files. Git manages its settings across 4 hierarchical levels: system, global, local, and worktree. The system level applies to every user and every repository on your computer. These settings are stored in a file in your machine's system administration directory, typically inside the etc. folder. The global level applies to your specific user account. These settings are stored in your user's home directory in a .git config file. This is where you configure your primary developer identity, global aliases, and default editor preferences. The local level applies only to the specific repository. The worktree level applies only to a specific linked worktree when you are checking out multiple branches simultaneously. This allows you to have unique configurations for different active checkouts of the exact same repository. Within these configuration files, you can modify several core behaviors of Git. For example, you can use the core.editor setting to change your default commit message editor. You can configure core.excludes file to point to a global gitignore file, ensuring Git automatically ignores system files like macOS DS Store or Windows Desktop ini across all your projects. You can also use the pull.rebase setting to force Git to always rebase your changes instead of creating merge commits when you pull from a remote server, maintaining a linear history across your entire local workflow. Moving beyond basic configuration files, Git provides file-level customization through Git attributes. Git attributes are defined in a text file named .attributes, which you place at the root of your repository and commit into version control. This ensures that these custom settings are shared by every developer on your team. A primary use case for Git attributes is managing end-of-line characters. Different operating systems handle line breaks in text files in different ways. Windows historically uses a carriage return followed by a line feed, known as CRLF, while macOS and Linux use only a line feed, known as LF. This mismatch can lead to entire files being marked as modified just because a developer on a different operating system opened and saved them. Resolving line-ending differences is done by using Git attributes to normalize text files. By declaring wildcard patterns in your Git attributes file, you can tell Git exactly how to treat specific files. For example, you can write a rule that maps all .js and .css files to the text attribute. This tells Git to automatically normalize these files to use line feeds when writing them to the compressed object database, and convert them to the operating system's native format when checking them out into the working directory. You can also use Git attributes to declare files as binary. By default, Git attempts to analyze files to see if they are text. If they are text, Git will generate line-by-line diffs. If you have large asset files like images, PDFs, or compiled WebAssembly binaries, you should explicitly mark them in your Git attributes file with the -diff attribute. This tells Git to completely skip line-by-line analysis for these files, preventing performance bottlenecks and keeping your commit diffs clean. For advanced workflows, you can use Git attributes to configure custom diff drivers. Imagine you have zip files or PDF documents in your repository. Under normal circumstances, Git cannot show you the differences between two versions of these files because they are binary. However, you can write a rule in your Git attributes file that pipes these files through an external command line tool, such as a PDF to text converter, before displaying the diff. When you run git diff, Git will run the tool in the background, convert the binary data to text, and render a beautiful, human-readable text diff in your terminal, allowing you to track changes in compiled or rich text documents. You can also use Git attributes to build clean and smudge filters. This is a highly advanced feature that allows you to modify the contents of files dynamically as they move between your hard drive and the Git database. Think of clean and smudge filters as automated security and formatting scanners. When you run git add, Git passes your file through the clean filter before hashing and writing it as a blob. When you run git checkout, Git passes the blob through the smudge filter before writing the file to your hard drive. You can use these filters to build keyword expansion systems. For example, you can write a smudge filter that automatically finds the phrase $$, in your source code and replaces it with the current system timestamp when you check out a file. You then write a clean filter that strips this timestamp out and replaces it with the raw placeholder before committing. This ensures that your source files on disk always display the latest checkout time, while your Git database remains clean and free of unnecessary modifications that would clutter your history with timestamp diffs. Automating task execution and enforcing local repository policies is handled by Git Hooks. Hooks are scripts that Git executes automatically when specific events occur in the repository's lifecycle. Hooks are split into client-side hooks, which run on your local computer, and server-side hooks, which run on the remote host. Client-side hooks are stored inside the hooks directory of your local .git folder. Because this folder is not committed to version control, client-side hooks are highly personal and must be manually installed or managed using external tooling like Husky. Let us trace the life cycle of a commit and examine the specific client-side hooks that run. First, executing the git commit command instantly triggers the pre-commit hook. This script runs before Git even prompts you for a commit message or creates a commit object. If the pre-commit script exits with a non-zero status code, the entire commit process is aborted. Teams use the pre-commit hook to run local automated tools. You can write a script that runs your code linter, executes your unit test suite, and scans your files for raw API keys. If your code fails the linter or tests, Git blocks the commit, ensuring that poorly formatted or broken code can never leave your local machine. Next, if the pre-commit hook succeeds, Git triggers the prepare commit message hook. This hook receives the path to the temporary commit message file and the source of the commit. You can use this hook to dynamically modify the default commit message template before the user sees it. For example, you can write a script that reads the name of your current branch, extracts the ticket ID, and prepends that ID to your commit message template, saving you from typing it manually. Once you write your message and close your text editor, Git triggers the commit message hook. This hook receives the path to your finalized commit message file. You can use this hook to enforce strict semantic commit message policies. If your script detects that your commit message does not match a specific regular expression, such as starting with a ticket number followed by an imperative verb, it aborts the commit. Finally, after the commit is successfully written to the database, Git triggers the post-commit hook. This hook cannot abort the commit. It is a notification hook. You can use it to trigger local desktop notifications, update project management boards, or log metrics. Server-side hooks run on the remote server hosting your bare repository. Because they reside on the server, they are highly secure and can be used to enforce absolute policies across your entire organization. Pushing code to a server triggers the pre-receive hook to validate references. The server's Git process feeds the list of references being updated to the pre-receive script. If the script exits with a non-zero status code, the entire push is rejected, and the client's push is completely aborted. This is the ultimate gatekeeper for your project's security and quality. Because it runs on the server, a developer cannot bypass it or modify its rules. To see how this works in practice, Let us walk through a detailed, narrative example of writing a server-side pre-receive hook to enforce a strict corporate push policy. Imagine your organization has a policy that prohibits any developer from pushing a commit that does not reference an active Jira ticket. You also want to block any commits that contain files larger than 50 megabytes and ensure that all committers use their official corporate email addresses rather than personal ones. Receiving a Git push prompts the server to stream the incoming pack file to a quarantine folder. The server then executes your pre-receive hook, passing 3 values to the script's standard input for each branch being updated: the 40-character SHA hash of the old revision, the 40-character SHA hash of the new revision, and the full name of the reference, such as ref/head/main. Your pre-receive script begins by reading these 3 values. It uses the old revision and new revision hashes to identify the exact range of commits the developer is attempting to push. First, the script loops through each commit in this range and extracts its commit message. It uses a regular expression to verify that the message contains a valid Jira ticket key pattern. If the script encounters a commit message like "fixed minor bug," it outputs an error message to the developer's standard error stream explaining that the commit message violates company policy and exits with a non-zero code, aborting the push. Second, the script inspects the author's email address for each commit. It checks the domain name of the email. If the author's email ends with a personal domain like gmail.com instead of your corporate domain, the script prints an authorization failure message and aborts the push. This prevents external identities from cluttering your corporate Git history. Third, the script queries the Git database to find the file sizes of all newly introduced objects. If it detects a binary file that exceeds 50 megabytes, it prints a warning explaining that large assets must be stored using Git large file storage and rejects the push. Only if every commit in the pushed range passes all 3 validation checks does your script exit with a code of 0. Git then accepts the pack file, writes the commits permanently to the bare repository, and moves the branch pointer. This demonstrates how a single server-side hook can guarantee absolute adherence to your organization's security, quality, and administrative guidelines. In addition to customizing Git's internal systems, software engineers must often integrate Git with other version control systems. In legacy environments, you may need to use Git as a client to communicate with a central server running Subversion or Mercurial, or execute a full migration to transition your legacy codebase to Git. Accessing a Subversion server with Git features is done using the bridge tool Git SVN. Subversion, or SVN, is a centralized version control system where history is stored as a sequential list of directory revisions on a single server. Running Git SVN clone followed by your SVN repository URL prompts Git to perform a series of translation steps. It connects to the SVN server, downloads every single historical revision one by one, and converts them into Git commit objects locally. It translates SVN's standard folder structure, where branches and tags are stored as physical directories named trunk, branches, and tags, into native Git branch and tag references. Once cloned, you have a fully functional Git repository on your computer. You can create branches instantly, commit locally, view history offline, and perform interactive rebases. The SVN server does not know you are using Git. It sees you as a standard SVN client. When you are ready to share your local Git commits with the SVN server, you run the command git svn commit. This command takes your local Git commits, serializes their changes to match SVN's directory-based structure, and commits them sequentially as new revisions to the SVN server. Keeping your local branch in sync with SVN revisions is handled by running git svn rebase. This command fetches the latest SVN revisions, translates them into git commits, and rebases your local unpushed work on top of them, allowing you to use modern Git workflows locally while maintaining compatibility with legacy centralized infrastructure. Eventually, your organization will want to migrate fully from legacy systems to Git. Migrating a legacy codebase, especially one spanning decades of history and gigabytes of data, requires a highly structured architectural strategy. The first step in a successful migration is author mapping. Git requires every commit to have a distinct author name and email address. Subversion, on the other hand, only records the system username of the committer, such as Smith. Preserving user metadata during SVN migration requires compiling an author mapping file. This file contains a list of your legacy usernames, with each username mapped to its corresponding Git identity. For example, you write a line that maps Smith to John Smith followed by his corporate email address inside angle brackets. When you import the history, Git reads this file and automatically rewrites the legacy metadata to match modern Git standards. Next, you run the migration import. For SVN, you use Git SVN clone with your author mapping file. Git will reconstruct the entire historical graph, preserving every tag, branch, and commit. Once the import completes, you must clean up the repository. Legacy version control systems were not optimized for size, and developers frequently committed massive database files, compiled binaries, or dependency folders directly to version control. Because Git copies the entire history to every developer's machine during a clone, leaving these massive files in your history will make cloning slow and consume excessive disk space. Cleaning up legacy bulk files from your imported history is done with Git Filter repo. This tool allows you to scan your entire imported history, identify large files, and permanently delete them from every single historical commit in your graph. You should also use Git Filter repo to convert legacy directory-based branches and tags into native Git references, and remove any legacy SVN metadata tags that Git SVN appended to your commit messages. Once the repository is lean and clean, you must validate the import. You check out different historical tags and compare their file contents to your original legacy repository, ensuring that not a single line of code was lost or modified during the translation. Finally, you establish a cutover plan. You lock your legacy server to prevent any new writes, perform a final synchronization run to capture any last-minute commits, and push your finalized, cleaned repository to your central Git hosting server. Your team can now clone their modern, high-performance Git repository and begin collaborating. This structured migration pathway preserves your organization's complete historical record, clean-shaven of bloated legacy files, enabling your team to confidently step into the future of software engineering. Elite mastery of Git requires looking past the porcelain commands to examine the system's architecture of the hidden .git database. Most developers treat Git as a black box of version tracking, memorizing sequences of high-level commands without understanding the database mechanics at play. Underneath its polished interface lies a simple, elegant file system built on graph theory, content-addressable key-value storage, and highly optimized binary serialization. By stripping away the high-level porcelain interface and examining the raw plumbing of the object database, references, pack file indexes, refspec mappings, transfer protocols, and maintenance subroutines, you will construct an absolute, unbreakable mental model of Git. You will no longer fear complex merge states, detached pointers, or database corruptions, as you will possess the precise knowledge required to diagnose, manipulate, and reconstruct any repository state directly at the binary level. Understanding this structural choices requires analyzing the division between plumbing and porcelain commands. This architectural design is a direct application of the Unix philosophy, which dictates that complex software should be built by combining simple, modular utilities that communicate through standardized text streams. When Linus Torvalds first designed Git in 2005, he did not set out to write a complete, user-friendly version control system. Instead, he wrote a low-level, content-addressable file system. This low-level engine consisted of small, highly specific command line utilities designed to manipulate files, calculate cryptographic hashes, and write index states directly to disk. These low-level, system-oriented commands are known as the plumbing, the user-friendly interface we interact with daily, comprising commands like branch, checkout, status, commit, pull, and clone, is known as the porcelain. Porcelain commands are high-level wrappers designed for human consumption. They manage complex user experiences, perform multi-step operations safely, and render output in colorful, readable terminal formats. For instance, when you run the porcelain command git commit, Git does not run a single compiled commit function. Instead, it executes a sequence of low-level plumbing commands in the background. It runs git write tree to package the current staging area index into a binary directory snapshot, then executes git commit tree to wrap that tree snapshot in author and timestamp metadata, and finally runs git update ref to move your active branch reference to point to the newly created commit object. By understanding how the porcelain maps directly to these plumbing primitives, you gain the ability to bypass the user interface entirely and script custom repository behaviors with total predictability. The foundation of Git's plumbing is the object database, located inside the objects directory of your .git folder. This database is a pure, content-addressable key-value store. In this database, the key is a cryptographic hash, and the value is the raw, compressed data payload. Git utilizes this model to store all project history, directory structures, file contents, and release metadata using only 4 primitive object types: blobs, trees, commits, and annotated tags. Every object written to this database is completely immutable. Once an object is saved, its contents can never be modified. If a single character in a file changes, Git does not patch the existing object. Instead, it writes an entirely new object with a different cryptographic hash, preserving the old version in perpetuity. Every object in Git's database is structured using a standardized binary layout. It begins with a human-readable header that defines the object type, followed by a space character, the size of the payload in bytes, and a binary null byte. This null byte acts as a strict delimiter. Everything following the null byte is the raw data payload. Once Git constructs this header and payload packet, it calculates the cryptographic hash of the entire sequence. Historically, Git has used the SHA-1 algorithm, which produces a 160-bit hash represented as a 40-character hexadecimal string. Modern Git installations are transitioning to the SHA-256 algorithm, which produces a 64-character hexadecimal hash, providing robust protection against cryptographic collision attacks while preserving the exact same structural object layout. Once the hash is calculated, Git compresses the entire header and payload packet using the zlib compression algorithm. It then writes this compressed byte stream to disk inside your objects directory. To store the file efficiently and prevent directory lookup bottlenecks, Git takes the first 2 characters of the 40-character hexadecimal hash to create a subdirectory name, and writes the compressed data to a file named with the remaining 38 characters inside that subdirectory. Let us analyze the specific structure of the first object type, the blob. A blob, which stands for binary large object, is the simplest object in Git. It stores raw file contents and nothing else. It does not store the file name, the directory path, the file permissions, or the modification timestamp. If you have 3 identical files in different folders of your project, Git does not write 3 objects. It writes a single blob object to the database because their content is identical and therefore produces the exact same SHA hash. This is the definition of content addressable storage. Data is retrieved solely by its cryptographic signature, completely decoupled from its physical metadata. Organizing these blobs into directory structures and linking them to file names is the responsibility of tree objects. A tree object corresponds directly to a directory on your file system. If you read the raw, uncompressed bytes of a tree object using the plumbing command git cat file, you will find it contains a list of binary entries. Each entry represents a file or subfolder within that directory. The tree consists of a file mode, which defines the file permissions, such as 100644 for a standard text file or 100755 for an executable, followed by a space, the object type, the binary SHA hash of the target blob or subtree, a tab character, and the file name. By nesting tree objects within other tree objects, Git constructs a cryptographic Merkle tree representing your entire project structure. Because every parent tree contains the hashes of its children, any change to a file at the bottom of the directory tree will alter its blob hash, which forces its parent tree hash to change, cascading all the way up to the root tree of your project. Chronologically linking directory snapshots and attributing authorship is handled by commit objects. A commit object is a plain text file that contains the core metadata of your repository's history. If you output a raw commit object, you will see it begins with a pointer to its root directory tree, written as the word tree, a space, and the 40-character SHA hash of your project's top-level folder. Below the tree line, the commit object lists its parent pointers. A standard commit contains a single line with the word parent and the hash of the preceding commit. A merge commit contains multiple parent lines, recording the dual ancestral paths that merged. The very first commit in a repository contains no parent lines. Below the parent pointers, the commit object records the author and committer metadata. Each line contains the name, email address, a Unix timestamp, and a time zone offset. Finally, after a blank line, the commit object stores your raw, unformatted commit message. The fourth object type is the annotated tag. An annotated tag object is structurally similar to a commit. It contains a pointer to a specific target commit hash, the target object type, the name of the tag, the tagger's metadata, a blank line, and your tag message. Unlike branch, which moves automatically as you work, an annotated tag is an immutable object in the database, designed to permanently sign and mark a specific release point in your history graph. While Git's object database is completely immutable, software development requires mutable pointers that can track our active work as we create branches and tags. Git manages this mutability through references, commonly referred to as refs. A reference is nothing more than a lightweight pointer to a commit object in your database. If you navigate to your refs directory inside the .git folder, you will find subdirectories named heads, tags, and remotes. If you open the file ref/head/main in a text editor, you will find it contains exactly 41 bytes of data, a 40-character hexadecimal commit hash, followed by a new line character. That is all a branch is. Creating a branch does not involve duplicating files or running complex database routines. It just requires writing a 41-byte text file containing a commit hash. When you make a new commit, Git writes the new commit object, reads your active branch file, and overwrites its contents with the new commit's hash. Tracking your active checkout is the job of symbolic references, most notably the head file. If you open the head file under normal development conditions, you will find it contains a reference pointer pointing to your active branch, written as refs/head/main. This is a symbolic reference because it does not point directly to a commit hash. Instead, it points to another reference file that in turn points to a commit hash. When you run git checkout, Git updates this head file to point to your target branch. If you check out a specific commit hash directly instead of a branch, Git writes the 40-character commit hash directly into the head file, entering a detached head state. This just means head is pointing directly to an object rather than a mutable branch file. As you work, Git also manages several short-lived, special-purpose references. Fetch_head records the commit hashes downloaded from a remote repository during your last fetch operation. Merge_head records the commit hash of the incoming branch during a merge conflict, allowing Git to know which parent pointers to write when you resolve the conflict and commit. Cherry_pick_head tracks the commit currently being reapplied during a cherry pick operation, and ORIG_head stores the commit hash you were on before you executed a potentially dangerous operation like a hard reset or merge, acting as a one-step undo button for your repository state. Over time, having thousands of individual branch and tag files in your refs directory can slow down file system performance, particularly on systems with high file access latency. To optimize reference lookups, Git compiles these individual loose files into a single flat file named packedrefs, located at the root of your .git folder. Each line in the packedrefs file contains a commit hash followed by a space and the reference name. When Git attempts to resolve a reference, it first checks for a loose file in the refs folder. If it does not find one, it scans the packedrefs file. When you delete a branch, Git safely removes its entry from this file, ensuring that reference resolution remains extremely fast. While loose objects and loose references are simple to understand, they are highly inefficient for long-term storage. A project with 10,000 files and a history of 1,000 commits would generate millions of individual loose files in the objects directory, consuming massive inode space and block-level file system storage overhead. To maintain a compact footprint and blisteringly fast disk performance, Git utilizes pack files. A pack file, stored with a .pack extension, is a single binary file that consolidates thousands of loose objects into a highly compressed stream. Each pack file is accompanied by an index file, stored with a .idx extension. The index file does not contain any file contents. Instead, it contains a high-speed lookup table mapping object hashes to their exact binary byte offsets inside the pack file. The binary layout of a pack file index is a masterclass in software engineering. It begins with a 4-byte header containing a unique index signature and a version number. Below the header is a 25 6-entry first-level fan-out table. Each entry in this table corresponds to the first byte of a SHA hash, from 00 to FF. The value stored in each index of the fan-out table is the cumulative number of objects in the pack file whose hashes start with a byte value less than or equal to that index. When Git needs to read an object, it does not scan the entire pack file, nor does it perform a slow sequential scan of the index file. Instead, it takes the first byte of the target object's SHA hash and reads the corresponding entry in the fan-out table. This instantly narrows the search space to a tiny segment of the index. Git then performs a highly optimized binary search within that segment to locate the object's SHA hash. Once found, Git reads the matching entry in the offset table, which provides the exact byte offset of the compressed object data within the binary pack file, allowing Git to execute a single high-speed disk seek operation to read the data. During the compilation of a pack file, Git runs its sliding window delta compression algorithm. Traditional compression systems analyze files individually. Git, however, exploits the deep historical relationships between your files. Because version history consists of files that are modified repeatedly over time, different versions of the same file share 99% of their contents. Compressing these objects efficiently begins by sorting them in memory by extension, path, and size. It sorts objects first by their file extension, then by their directory path, and finally by their file size. This sorting heuristic ensures that different historical versions of the exact same file are placed adjacent to each other in the memory queue. Next, Git passes a sliding window which defaults to 10 objects over this sorted list. It compares the binary content of each object in the window to the other objects within the window. If it finds two highly similar files, it calculates their binary difference, or delta. Instead of writing the complete content of both files to the pack file, Git stores one full version of the file, known as the base frame, and then stores the subsequent version as a tiny list of binary insertions and deletions relative to that base frame, known as the delta frame. Crucially, Git's delta compression is directed backward in time. Git stores the most recent active version of your file as the complete undelted base frame and compresses older historical commits as deltas relative to that modern base. This is because you are far more likely to check out, read, or compile the latest version of your codebase than an ancient release from years ago. By storing the modern version intact, Git guarantees that checking out your active branch requires 0 CPU cycles for delta reconstruction, keeping your daily workflow extremely fast while compressing your historical archive into a fraction of its original size. Varying how branches sync between local databases and remote hosts is controlled through refspecs. A refspec is a powerful, highly structured format string that defines the exact mapping between the reference namespace of a remote repository and your local reference namespace. The basic grammar of a refspec is written as an optional plus sign, followed by a source reference, a colon, and a destination reference. If you inspect your local repository's config file, you will find the default fetch refspec for your remote server. Fetch equals +head//colon/ref/remote/origin/**. Let us analyze this format string step by step. The colon acts as a strict boundary. The left side of the colon, ref/head/*, defines the source branches on the remote server, where the asterisk acts as a wildcard matching any branch name. The right side of the colon, ref/remote/origin/*, defines where those branches should be written on your local hard drive. This is the exact ref spec that maps the remote branch named main to your local remote tracking branch named origin/main. The plus sign at the beginning of the ref spec is a force flag. Under normal circumstances, Git will only update a reference if the incoming commits represent a clean fast-forward merge. If another developer has rewritten history on the server and force-pushed their changes, your local fetch operation would normally be rejected to protect your history. The plus sign tells Git to bypass the safety check and force update your local remote tracking branches to match the server state exactly, ensuring your remote tracking branches always reflect the absolute truth of the server. You can also use custom ref specs to design advanced deployment and testing workflows. For example, if you are building an automated continuous integration server that only needs to test staging branches, you can write a ref spec that maps ref/head/ref/remotes/origin/staging. This configures Git to completely ignore all other branches on the server during a fetch operation, dramatically reducing network transfer times and disk usage on your build agents. Ref specs are equally powerful during push operations. If you want to push your local main branch to a branch named release on the remote server, you run the command git push origin followed by the ref spec main:release. If you want to delete a branch on the server using raw plumbing mechanics, you can run git push origin followed by a ref spec with an empty source side, written as :branch name. This tells Git to push nothingness into the remote branch, which the remote server interprets as an explicit command to delete the reference from its disk. When Git transfers these ref specs and pack files over the network, it communicates using highly optimized transfer protocols. Historically, Git supported the DUM protocol, which was a simple, read-only mechanism that treated your repository as a static collection of files served over standard HTTP. When a client attempted to clone over DUM protocol, it had to download individual loose objects and pack file indexes one by one, parsing them locally to figure out what files to request next. This resulted in terrible latency and network congestion. Modern Git relies entirely on the SMART protocol, which exists in two versions, version 1 and the highly optimized version 2. The SMART protocol is a bidirectional, stateful conversation that runs over SSH or Smart HTTP, utilizing specialized server-side helper processes named Git Upload Pack and Git Receive Pack. Fetching changes prompts your local client to connect and invoke the upload pack process on the remote server. In version 1 of the protocol, the server begins the conversation by sending a massive, unprompted advertisement of every single reference, branch, and tag it possesses, along with their current commit hashes. For massive enterprise repositories with millions of branches, this initial reference advertisement can be dozens of megabytes in size, creating a massive performance bottleneck before any actual code is transferred. Version 2 of the SMART protocol solved this issue by introducing stateless, capability-based negotiation. In version 2, when your client connects, the server does not advertise its references. Instead, it sends a simple, compact list of its supported capabilities, such as protocol version, object filtering, and command routing. The client then sends a specific command, such as lsrefs or fetch, along with precise filter arguments. Once the references are resolved, the client and server begin their graph negotiation. The client sends a list of commit hashes it wants, and a list of commit hashes it already has at the tip of its local branches. The server's upload pack process reads these lists and performs a rapid graph traversal in memory. It identifies the exact boundary commits where your local history and the server's history diverge, calculates the minimal set of objects required to bring your local repository up to date, compiles them on the fly into a single pack stream called a thin pack, and streams it over the network. This ensures that every fetch or pull operation transfers only the absolute minimum amount of data required, maintaining blazing fast performance on any network. Despite Git's robust systems design, repositories can occasionally accumulate orphaned files, loose references, and database fragmentation. To maintain a clean, high-performance footprint, Git provides automated maintenance and data recovery subroutines. When you perform rebases, hard resets, or force pushes, commits that were once part of your active branch history can become detached. Because no branch, tag, or reflog pointer points to them, they are no longer reachable during a standard graph traversal. These are known as dangling or loose objects. Git does not delete these objects immediately, acting as a critical safety net against accidental data loss. Instead, they remain in your objects directory until Git runs its garbage collection routine, which you can trigger manually by running the command git gc. During garbage collection, Git performs a comprehensive optimization sweep. First, it packs all loose reference files into the packed refs file. Second, it consolidates your loose objects into optimized pack files using sliding window delta compression. Third, it runs the prune subroutine. The prune subroutine scans the creation timestamps of all dangling objects. By default, Git will not delete any dangling object unless it is older than 14 days. This 14-day grace period is a crucial safety mechanism. It ensures that if you are currently running a long rebase, a complex merge, or a cherry pick when garbage collection is triggered, Git will not delete the intermediate, unreferenced objects you are actively working with. If you have permanently lost a commit due to an accidental hard reset or branch deletion, your first line of defense is the reflog. The reflog is a local ledger stored in your .git/logs directory. It records every single transaction of your head pointer and your local branch pointers. Unlike Git log, which displays the chronological history of your commits, the reflog displays the chronological history of your local actions. Every time you check out a branch, commit code, pull changes, or perform a reset, Git appends an entry to the reflog file. If you run the command git reflog, Git displays this ledger. Once you find the action you want to revert, you copy the associated commit hash, create a new branch at that hash, and your lost work is perfectly restored. If your reflog has been cleared or expired, which happens by default after 90 days, you can perform a low-level database recovery using the file system check utility Git fsck. When you run Git fsck with the --lostfound flag, Git performs a complete low-level cryptographic sweep of your objects directory. It starts at every active branch pointer, tag pointer, remote tracking branch, and remaining reflog entry, and traverses the entire history graph downward through every tree and blob. Any object that is not visited during this traversal is flagged as a dangling object. Git fsck writes these dangling commits, trees, and blobs to the .git/lostfound directory, sorting them into commit and blob folders. You can use git cat file to pretty print these files, locate your lost code, and restore it to your active branch history, bypassing any porcelain-level failures. Controlling low-level operations dynamically is done through system environment variables. By setting these variables, you can override your global configuration files and programmatically manipulate how Git executes commands. The variable git_dir allows you to specify a custom directory for your repository's database. By default, Git searches for a .git folder in your Active Directory. If you set git_dir to a different path, you can keep your Git database on a separate, encrypted drive while keeping your working directory on your local solid-state drive, providing enhanced security for sensitive code bases. The variable git_work_tree allows you to specify a custom path for your working directory, completely decoupling your physical source files on disk from your Git database directory. The variable git_index_ file allows you to specify a custom location for your binary staging area index. This is highly useful for advanced automation scripts that must perform background staging operations without modifying your active, local staging area. The variables git_object_directory and git_alternate_object_directories allow you to configure custom and shared object storage locations. If your company hosts many massive repositories on a shared server, you can configure them to share a single alternate object directory, preventing the duplicate storage of shared framework blobs and keeping server disk usage extremely low. For metadata manipulation, you can use the variables git_author_name, git_author_email, git_author_date, git_committer_name, git_committer_email, and git_committer_date. These variables allow you to programmatically rewrite the authorship and timestamp details of a commit on the fly, which is highly useful for continuous integration agents, release bots, and automated code generation systems. Finally, for low-level system debugging, Git provides robust tracing variables. By setting git_trace to 1, Git prints detailed debugging logs showing every system call, child process, and internal command execution to your terminal. By setting git_trace_performance to 1, Git logs the exact execution time of every internal subroutine, helping you identify disk bottlenecks and slow hooks. By setting git_trace_packet to 1, Git prints the raw hexadecimal packet streams of the smart protocol in real time as your client communicates with the server. And by setting git_curl_verbose to 1, it outputs the complete SSL handshake and header negotiation details of your HTTP connections. This gives you absolute system-level visibility into every byte of data that enters or leaves your repository. By mastering these low-level internals, from the binary header and payload layout of objects and the structural design of packfile indexes, to the grammar of refspecs, stateless smart protocol negotiation, low-level FSCK data recovery, and runtime environment variables, you elevate your engineering capability. You are no longer just a user of version control. You are an expert of repository architecture, fully equipped to manage, secure, automate, and debug the most complex software delivery systems in the technology industry. Thank you for dedicating your time to mastering Git and GitHub with us today. Congratulations on completing this comprehensive masterclass. You have successfully journeyed from the basics of version control to the deep internals of Git's content addressable storage, object databases, branching graphs, remote protocols, and advanced repository recovery techniques. By building these robust mental models, you have equipped yourself to tackle any code-based challenge like a seasoned staff engineer. Keep learning, keep building, and we will see you in the next lesson.